So good morning, everyone, to those online, to those in person. Actually, I guess something is going on the traffic today in Rio de Janeiro. I know Ariana is there, but let's wait for her to reappear. Oh, there she is. Okay, great. So really can start the program of today. As you know, we will have Ariana Cortese online, then Eduardo Cipriano online, and then the next two talks are in person. Sorry if I'm repetitive because I don't remember the faces of everyone that were here, but just in case, as you know, we don't have funds for the coffee break. So we are collecting donations. If anyone wants to contribute, there is a little box outside, and there is a Pix number that you can transfer to our secretary, and she would handle that, okay? That being said, we can start the program of today. Also, for those in person, we plan to have a happy hour after the meeting. So the place to go is Belmonte Urca. It's a bar in a very nice place for those of Rio de Janeiro, you know. And we will make a list so that those interested, we can make a reservation. They have like a card there, so you pay what you consume. So it makes life easy for everyone. So everyone is invited. The idea is to go after the closing. We'll have a round table, by the way. There is it's written here. So yeah, we'll have the round table. So after the round table, we'll walk and we'll get there about 6 p.m. That's the plan. Okay, so those interested, let us know. We'll have a list there. Okay, so without further ado, let's start the program of today with Ariana Cortese from the Federal University of Rio de Janeiro about planetary nebula spectrograph survey of these galaxies, recovering stellar kinematics to up to 8 effective radii. Thanks, Ariana, for being there. You are muted, Ariana, you are muted now.
My fault. Now you can hear me.
Yes, perfectly.
Great. Okay, so I would like to thank the organizer for the possibility of presenting this work. And this is a work that's a collaboration for people from the Nottingham University, where I did my PhD thesis, as well as people from the Observatory of Valongo in Rio de Janeiro and some people from Max Planck in Munich. And so this work, I will try to present several results, both from kinematics of planetary nebulae for especially lenticular galaxies. So, okay, just a brief introduction. We know that the universe as we see it today comes from an evolution from a very homogeneous and isotropic initial conditions that brought to the multitude of galaxies with such beautiful morphological shapes that we can see nowadays. And we also know, especially through numerical and hydrodynamical simulation, that there is a connection between the evolution, the clustering of dark matter while time is passing, and the formation of galaxies, where we have galaxy clusters at the junction of filaments of dark matter when the baryonic matter fall in the dark matter halos. So, as I was saying, nowadays we see a large diversity in galaxy morphologies, and the first morphological classification is due to Hubble. Presented here is a very well-known plot where we have elliptical galaxies on the left with different ellipticities. We have the lenticular galaxy at the apex of these twinning forks, and then we have the spiral galaxy bar and unbar. I underline here that also lenticular galaxy can be bar and unbarred. So in here I also show Hubble looking at an image of a galaxy printed as they used to do back then, also to show how much our technology evolved during time. So it is a telescope that Hubble used, and this has a strong consequence in the way we look at galaxy. So a galaxy image depends a lot on the depth and resolution, so resolution of the instrument and depth of the observation. So this is an example of a lenticular galaxy, which is NGC 5866, has seen from 2 mass in J-band. But we can look at the same galaxy using the Hubble Space Telescope, and we can see how different it could appear to us due to the increase in resolution. It is also possible to observe the galaxies via multiple observation and accurate subsequent combination of the images to see their very deep and faint outer parts. So this is an example done using the Schulman telescope, which I show here with a very young astronomer. And this is the result of this type of studies, where it's possible to see the satellites being accreted from the main galaxies in this almost X shape. So again, morphology is something that can be connected to the depth and resolution of the image, so it has to be taken carefully. Another important fundamental property of galaxies is kinematics, and one very powerful way of studying galaxy kinematics is using IFU data. This is an example of IFU data that shows that on the X and the Y axis we have the image of the galaxy, while on the third axis we have the wavelength dependence, so that pixel by pixel we can recover a spectra of the galaxy in that location. And using this type of instrument, several surveys have been exploring galaxies, early and late type galaxies, so elliptical, spiral, and zero, in the local universe, as Sauron, Atlas 3D, and the Khalifa survey, among others. And in this plot, that's from Falcon Barroso 2015, I show the relation between the angular momentum and the ellipticity of the galaxy. So galaxies are color-coded according to their morphological type. So elliptical are red, and zero are orange, and then different type of spiral from yellow to blue. And also you can see there are 2 lines that I will describe better in the next plot, but these 2 lines separate objects between what are called slow and fast rotator. And it's possible to see that slow rotator have lower value of lambda, which is lambda is proportional to the ratio between rotational motion of stars and dispersion velocity of the stars in a galaxy. So it's telling us how hot is the disk. So if it is dominated by rotation or if it is dominated by random motion. In the first case, lambda is high, and this happens generally as shown in this plot for spiral galaxies and the lenticular galaxies, while in elliptical, generally lambda is low, and they are in fact dominating the slow rotator part of this plot. And using this information, the Hubble diagram has been expanded so that to include also the kinematics in the classification. So we have on the x-axis the presence of stellar disk, which is related to the motion of stars within the galaxy. So we have slow rotator, elliptical on the left, and lenticular galaxies, and E5, the more elongated elliptical galaxies on the right as fast rotator. On the y-axis, we have the presence of spiral arms, so that it's possible to have spiral which are fast rotator with spiral arms. And in here, they are shown both phase on and edge on. So all of this is important because one of the key elements that brought to the understanding of the existence of dark matter has been indeed studying the rotation curve of spiral galaxies. Here I'm presenting a plot from, I think, one of the first works of Vera Rubin, where she presents the rotation velocity versus the distance from the center for a sample of spiral galaxies. And on the right is a picture of her at the telescope. So what they found is that the rotation velocity remains constant with radius and doesn't fall following a Keplerian behavior. And that's due to the presence of dark matter, which is particularly important to study the outer part of the stellar disk, because it's where dark matter presence becomes more evident. And in fact, it's not the case that these first work were based on spiral galaxies. In fact, the H1 gas disk offers a great way of exploring the velocity to the larger radii in a galaxy. And I want to stress this point, also including a reference from a work of Romanowski and Fall of 2012, where they show to which radius we need to extend in order to cover, in order to study a different fraction of the angular momentum of a galaxy. So in the plot on the left, on the x-axis, we have the ratio between the radius and the effective radius of the galaxy, which is the radius that encloses 50% of the galaxy light. And on the y-axis, we have the ratio of a given quantity divided for its total value. On the top, for disk galaxies that are described with an exponential profile, and on the bottom plot for galaxies that follow a devacular light profile. And what is possible to see is that the stellar mass is described by the dotted light, the dotted line, while the specific angular momentum is the field line, and the angular momentum is the dashed line. For spiral and disk galaxies, it's possible to see that already at 4 effective radii, we reach more or less, we are able to study almost all the angular momentum, while for elliptical galaxies, we need to extend to larger and larger radii in order to really prove the angular momentum and therefore determine the quantity of dark matter within the galaxy till large radii. And for this reason, the planetary nebula spectrograph has been designed. This is an instrument that uses planetary nebulae to trace galaxy kinematics out to large radii. The PI now is Magda Arnaboldi at ESO in Munich, and before the instrument has been designed by Nigel Douglas. And in here on the right, on the top, is presented the design of the instrument, which I'm going to explain in 1 second, but first we should look on the left at the spectrum of a typical planetary nebula, which is the object that is, I don't know if you can see my cursor is here up on the right. Planetary nebulae are stars as the sun, so low mass stars at close to the end of their life, when they have ejected the envelope of carbon and oxygen, and the ultraviolet light emitted from the inner residual that will become a white dwarf at the inside of the nebula is highlighting the oxygen and the H-alpha elements within the nebula. So that makes the spectrum of the planetary nebulae very specific, where it's possible to see the doublet of the oxygen tree and the H-alpha line. So the idea of the planetary nebula spectrograph was to have an instrument that really fine-tuned to find planetary nebulae. And as you can see, the light will pass through the telescope, and when reaching the two spectrographs, the two slits, the slits are divided in 2 arms, the left arm and the right arm, where the mirror is shifted of 180 degrees. The result of this setting, as shown on the bottom right, is that especially the very bright part of this plot, the shift caused by the velocity of the planetary nebulae is driven toward the left side on the left arm and toward the right side on the right arm because of the design of the instrument. So this instrument is also equipped with a O3 filter, so that when the planetary nebulae light pass through it, planetary nebulae will look like this object here within the green circle. They look like dots. On the other side, stars that have a continuum and not only this specific emission line look like star trail. Therefore, this instrument allows you to identify a planetary nebula, and by measuring the distance between the right and left image, as I'm going to show you now in this plot, you can extract the position of the PNE and its velocity. So these are two examples of images, spectral images, obtained with the FNS. This is a work from Napolitano et al. In 2009 for NGC 4494. And you can see different objects within different boxes. So if we look, for example, at this orange box, we can see that the same dots that are all planetary nebulae are shifted with respect to each other in the left and the right arm. So here is here, and here is here. This one also is shifted. So the shift is proportional to the velocity of the planetary nebula, and between the 2 points is the position. So here I'm giving some reference of works that have been done using the planetary nebula spectrograph, from the first work from Nigel Douglas in 2003. There are several other works that studied dark matter in elliptical galaxies, as well tracing the halo of galaxy out to large radii. I always worked especially with lenticular galaxies, and there are also very recent work from Pulsoni et al. Exactly studying the angular momentum of early type galaxies. So, okay, I will now focus especially on lenticular galaxies that, as you remember, are at the apex of the Hubble tuning fork. And I'm going to show you during the talk why we think they're such interesting objects. And here I'm showing the sample we have. There are 6 lenticular galaxies shown here, among which some have bars. And then we have recently added these other objects where we also have 2 spiral galaxies. Is NGC 891 here on the right, and another one that I think is 7932 here on the left, which is a barred spiral. So what are the main characteristics of lenticular galaxies? First of all, they have a bulge. There are a lot of discussion in the literature whether the bulge of a lenticular galaxy is bigger or not of the bulge of a spiral galaxy. I put here a reference, but there is not a consensus, I think, among the astronomers. Then they have a disk that doesn't have arms. And when you combine these 2 components, you can recover the isophotal shapes of lenticular galaxies. And there are several formation scenarios. First one, as you could have imagined even from the previous plot, is that lenticular galaxies are quenched spirals. So the idea is that when a spiral galaxy falls into the cluster, due to the interaction with the hot intra-cluster group, will lose its spiral arms, will be stripped by its gas, and will remain only with the bulge as a disk, as a lenticular galaxy. This has been proven also due to several work, even from Dressler in the 1980s, and still now it has been found, as shown in this plot, that if we look in a cluster at the distribution of spiral, elliptical, and lenticular, where spiral here is the blue line, elliptical, the red line, and the 0, the dark line, it's possible to see that the number of the 0 increases towards the center of the cluster and the number of spiral decreases. Moreover, a similar effect is found when looking at the total number of spiral and the zero in cluster with redshift. Cluster at higher redshift present more spiral galaxies than cluster at low redshift. So the first idea is that a zero could be quench spiral galaxy. And this is a very simple scheme where the galaxy lose the spiral arms and remain with the bulge and the disk. The problem is that we do find isolated lenticular galaxy. So clearly there must be another formation scenario for a lenticular galaxy, which is true mergers. For example, as in several work of Ehrlich and Moral and this group that did several simulations of merger of lenticular galaxies with different masses and different parameters of the interaction. And it's possible to see that during the interaction, the outcome, so the remnant of the merger, is an object that has, as shown in this plot, similar characteristics, isophotal characteristics, as a lenticular galaxy. So it has a bulge and a disk. For example, some might still have a remnant spiral arm, which is something that actually is possible to find sometimes in lenticular galaxy. Okay, so a second mechanism of formation could be that lenticular galaxies are merger remnant. Now, how can we prove this? One possibility is exactly studying the kinematics of stars within lenticular galaxies using planetary nebulae, because as I was explaining before, it allows us to trace the kinematics out to very large radii. So here is the same sample I was presenting before. Planetary nebulae are shown in their position, color-coded according to their velocity. So blue are blue shifted and red are red shifted. This is the first sample presented. And now we are expanding to a second sample of planetary nebulae. Okay, so we also wanted to be able to separate the bulge and the disk components, because what can happen is that since the bulge is so prominent, if you study this galaxy as a unique system, you might find a wrong kinematical profile due to the contamination of bulge planetary nebulae to the disk kinematics. To do so, we first perform a photometric decomposition of the galaxy images. So this is a simple model made with Galfit for the K-band image of these galaxies, where we have the image on the left, the model on the center, and the residuals on the right. And it was a model that would allow for a disk and a devacular bulge. Then for barred galaxies, this is a work that I especially have done with Karine at the Observatory of Valongo, we also model the bar within the galaxy so that we take into consideration the bar component and we can really retrieve the disk light profile. So here I show the image on the top left, the model in the center, the residual on the top right, and on the bottom, the three components, the bulge, the disk, and the bar. And what is nice to see is that when we look at the surface brightness profile of this galaxy versus the radius, where the surface brightness is described for the K2 mass band by these squares, we can see that it matches very well the total model we created, which is the black line. We have then the three components, in red the spheroid, in blue the disk, and in magenta the bar. And over it, we overplot the number density of planetary nebulae in different bin, which are these green dots. So it's possible to see that the planetary nebulae we have really follow the light profile of the galaxy and are good tracers of the total stellar kinematics of this galaxy. So then, by dividing the bulge image for the total image, we created something that we call the F-map, where at the position of every planetary nebula, we can assign to it a probability of belonging to the bulge that goes from 0 to 1. In here, the darkest area is where the disk dominates, and the clearer area is where the bulge dominates. The black lines show the 50% separation between the two components. And this histogram shows the distribution of the probability of belonging to the bulge and the disk based purely on photometry. It's possible to see here in the middle that we have a lot of objects with a probability of 0.5. So very hard for photometry only to know if they are disk or bulge objects. But we included this probability, which is this Fi in this equation, in a likelihood equation that we use to find the best fit for the kinematics of the galaxy. And we could recover now the probability of belonging to the disk and the bulge using both photometry and kinematics. And we can see that this peak at 0.5 decreases, and we can better separate the planetary nebulae from spheroid and disk object. So we are now able for each galaxy to recover the rotation in the disk, which is what is shown in the top panel of each plot. So these are 6 different galaxies. We can recover the dispersion velocity in the disk, both the radial and azimuthal component, and the dispersion velocity in the spheroid. We are assuming that the spheroid is not rotating the bulge. And this is the full sample. I'm going to show just one big, so it's easier to be seen. This is the galaxy I was showing at the beginning, 5866. It's possible to see that in the inner radius, which is here on the x-axis, the rotation velocity is quite constant, while we have large error bar in the outer part. And this is due to the fact that in the outer part, the majority of the planetary nebulae are associated to the spheroidal component, which could be either the extension of the bulge or the halo. We can see here the dispersion, both azimuthal in blue and radial in red, also quite constant with radius and decreasing, and the dispersion in the spheroid. Okay. So what we can do now is that we can calculate for each one of these galaxies the ratio between the rotation and dispersion velocity, the azimuthal dispersion velocity in the disk, at a given radius. We chosen 3 disk scale lengths for both lenticular galaxy and spiral galaxies from another work always done with planetary nebulae. And it's possible to see that our lenticular galaxy have a kinematic that is slightly hotter than the one of spiral galaxy, but yet V over sigma is around 3. And I point this because when we compare with simulation, as I'm showing in these plots on the right and top of this panel, we can see on the top results from simulation of minor merger for Bourneau et al. 2005. Again, is a similar plot. We have velocity versus radius. We have the circular speed, the rotation velocity here in dashed, and then the 2 dispersion velocity. It's possible to see that for a merger of 4.5 to 1, so the merger, the ratio between the 2 galaxies, we get a V over sigma around 1. And only for a merger of 10 to 1 mass ratio, we get a V over sigma higher than 1. And something very similar is shown here in this plot from Tapia, which is also in the group that we were seeing before of merger of galaxies to produce lenticular. When we look at the ratio between dispersion and the rotation, we will have value around 1 of V over sigma. So they seem to be hotter than what found in our data. And instead, this last plot I'm showing now shows the result of V and sigma, so rotation and dispersion versus radius, for a simulated object falling into groups. So instead of being a big cluster environment, it's the group environment. So it's the tidal interaction among galaxies. and they are colored differently according to time from infall, from going from T0 when they just enter to higher time as going till 5.6 gigayear after infalling. And the effect of the tidal interaction is to decrease the rotation velocity and increase the dispersion velocity in the disk, and reaching a value of V over sigma similar to what we find for our lenticular galaxies. Okay. Then there is a final, at least there are several, probably other, even like Aegean feedback, but there is another way of creating lenticular galaxies that we find very interesting, which sees lenticular galaxy being a primordial object born around redshift 0 around equal to, redshift z equal to, from the merger of clumps within the galaxy. So as we know, a galaxy at high redshift are way less smooth and structured than galaxy at low redshift, and they present a very clumpy structure. The merger of these clumps, for example, is also known to be responsible for the formation of the bulge in galaxies. And what we propose is that you could form both the bulge and the galaxy disk, creating something very similar to a lenticular. So lenticular galaxy in this case will be primordial galaxy. And this has been shown using a simulation, numerical simulation for galaxies with different Tomre-Q parameters. So this is a result from the simulation. We have the starting galaxy with different Q, so different value of Tomre-Q. When this parameters is lower than 1, the disk is unstable. And of course, the lower, the most unstable it is. So the disk will break in different clumps that would subsequently merge to form both the bulge and the disk of the galaxies. And when we compare V over sigma versus radius for the simulated objects that are the black circle and the open red square, with results from planetary nebulae spectrograph kinematics, which are these galaxies shown here, we see that especially for NGC 7457, that is magenta asterisk, and NGC 2768, we find a very nice follow, like they really trace each other, suggesting that some of the lenticular galaxy could really be the result of this, could be these primordial objects, so that lenticular galaxy will be a composite mosaic of formation scenarios. So I'm including this slide that I found while preparing the talk from some old slides, as you can see from the phrase that I wrote. And unfortunately, only 2 of my wishes back then became true. But I'm going to read, basically, this is the final sentence of a paper drafted by Aaron Romanowski, where he suggested that while ellipticals are the result of intense histories of mergers, and massive spirals instead are due to later accretion and quieter accretion of cold gas, lenticular galaxy will be objects that didn't participate to neither of these events, and will actually be living fossil of a primordial era of galaxy formation. To conclude, I wanted to show something that I think is very interesting, which is the Tully-Fisher relation, in this case for both lenticular and spiral galaxy. So the Tully-Fisher relation plot the absolute magnitude, in this case a K-band, versus the circular speed of a galaxy. We have in blue spiral galaxies, and our lenticular galaxies are here color-coded with different symbols. Some are barred and others are not barred, and they seem to follow a parallel line to the one of spiral galaxies, even if this becomes less evident while they become smaller, so fainter and with lower circular speed. And actually, there is a similar result from Romanowski and Fall, where they compare the stellar mass versus the specific angular momentum of galaxies, and they can show that there is a kind of a subsequent line, parallel line, depending on the galaxy morphology and the B over T, so bulge to total light ratio, going from pure disk to pure spheroid.
Ariana, just to tell you, let you know that you have 5 minutes.
Okay, well, I have finished anyway. And so basically, I wanted just to propose several things that we could explore together. The first one that I think will be very interesting will be to recover the dark matter profile using this data of both barred and unbarred lenticular galaxies. That's something that we started working on with Karine Del Mestres Menendez when I was her postdoc at Valongo. And another thing that I think will be very interesting to again see which is the role of the bar in this physically motivated classification of galaxies, so that does the bar also have a role, or is really just something related to the presence of the bulge and the disk? And finally, also comparison this with simulation. That's something we are doing now to see if we can recover the lenticular galaxy formation tree. So this is my email, if you wish to contact me. And I thank you a lot for your attention. And yes, if you have any question or doubts.
Okay, we have time for questions. Questions from the audience here. Or questions online. If you want to ask a question online, just unmute yourself. Okay, I have some basic questions. How do you identify these? I mean, you showed a nice picture of like a S0 with these colorful dots where the planetary nebula are. How do you identify this planetary nebula in the images?
Yes, it's done using the this counter dispersed spectrograph. That's a planetary nebula spectrograph. That's basically what you have is very similar to these. So you have an image, which is a spectral image. So you have that everything is kind of, so the x-axis here is wavelengths. So you have that everything is dispersed, but since we use an O3 filter, we only get, let's say, the wavelength range in O3. And as you can see from the planetary nebula spectrum, maybe you can see, if you cut here in the O3 region, planetary nebulae only have this double emission and don't have a diffuse light, while stars, as is shown here, have diffuse light. So PNE really looks like dots in these images, and stars looks like trails. Moreover, since you have, we have two images, one in the left and one in the right arm of the instrument. Let me show this better. So this is the diagram of the planetary nebula spectrograph. The light comes here and it goes through the O3 filter, here actually maybe, and then here it reaches these two slits, which are have different angle. So the light is dispersed in opposite direction. So it can be dispersed toward the right or toward the left. So when we look at the final image, comparing the left and the right image, you can see that if it's a true planetary nebula, you will see it in both arms, so in both images, as in this case, and you will see it kind of jumping because she's shifting from one side to another. And you'd recognize it against stellar light exactly because they are dots and not streams, like they're not long.
Right, thank you. So, okay.
Did I?
No identification spectroscopic, okay.
Yes, and then you get the velocity which is proportional to the shift in the position between the left and the right arm. So that's how we managed to go to this, because the shift is proportional to the velocity. And since they shift in the opposite direction in the two arms, when you measure this distance, you measure the velocity of the planetary nebula.
Right, right. Cool. Very interesting. So there are other instruments that do this cross dispersed spectroscopy, right? Are they being used also for planetary nebulae?
I think so. I know now actually there are also surveys of planetary nebulae using MUSE in Fornax cluster, for example. So the thing is that this instrument was optimized for planetary nebulae. So it was really done. For example, it didn't have the necessity of follow-up, because what you will do first could be first identifying them and then finding their velocity. While this one, since it has two arms, you do both steps in one goal.
Right. More questions? Yes.
Tiago. No.
Hi, Ariane, it's Amanda here.
Hi.
I'm not sure I missed the very beginning of your presentation. I'm not sure if you mentioned, but why did you expect to have this planetary nebula so far in the galaxy?
Well, planetary nebulae are just common stars, let's say. So you, especially in elliptical and lenticular galaxies that tend to have older stellar population, you expect to have them both in the disk and in the bulge. The cool thing about them is that they are independent from the surface brightness of the galaxy. So while, especially in, in lenticular galaxy or elliptical galaxy, differently from spiral, the surface brightness profile decreases rapidly while you go far from the center. The PNE can be seen even if very far out, because they have this very specific spectrum, and so you can spot them. Of course, the number density of PNE, which is what is shown here, the number density decreases with radius. So in the inner part of the galaxy, you tend to have more PNE than in the outer part. But you can really find them even in the outer part. So for example, in this case, the light of the galaxy, and here around 70 arc seconds from the center of the galaxy, where we find planetary nebulae till very far out. So we, depending on the mass of the galaxy, we can go out to up to 8 effective radii. They're similar to globular clusters in this sense. They can really allow you to map the galaxy kinematic in the very faint outer part.
Very nice. And how far are these lenticular galaxies? What redshift they are?
Local. So the planetary nebulae only see galaxy up to 20 megaparsec distance. So that's the backside, like, you know, to be able to see a planetary nebula, it cannot be too far away. So they tend to be very close by objects.
Okay.
Thank you. I know Thiago wants to make a comment or ask a question, but since we are on that specific slide, I wanted to ask a question about that. So this plot is for a specific planetary nebula or some kind of combined profile?
So this galaxy is...
Sorry, galaxy.
Is a specific one. Let me remember which one is it. Is this one? I think is yeah. I have to check. It's a barred one. Yeah. I do it for everyone because it's most probably this one. So it's NGC 936. So for every galaxy, it's possible to. We actually do it as a sanity check to make sure that the number of PNE we find is consistent with the extrapolated profile of the galaxy light.
Okay. Yes, Thiago?
Hi, Diana. Great talk. Thanks. This is This is just a simple question still on the instrument, but in principle, you would find anything with a high enough equivalent width in O3, right? Any kind of
Yes.
strong nebular emission, not just planetary nebula. I don't know if you
So-
have any way of separating what type of object it is.
So, okay, we have contaminant, of course. There is this coincidence for which QSO at high redshift tend to have a spectrum that is extremely similar to low redshift planetary nebulae. So you might have some objects that are actually quasar, as well as they could be H alpha emission. If they are H alpha emission, well, first of all, in generally with early type galaxy, with things we don't have too much. And also when you look at the image here, or they tend not to be, they are not very circular, because a planetary nebula will just have the profile of the PSF in that specific image because they're point-like sources. While the H alpha emission could be more extended or could have some streams. So we try to distinguish them using parameters of the shape of the objects. So what we do practically is that we first median subtract the image, then we extract all the objects using S extractor, and then we use a combination of parameters to try to identify only the PNE. But you might have contamination. If it is a quasar, you realize it because when you get then the velocity, it has a very high velocity, which is clearly not belonging to the galaxy. With H alpha, it's more tricky, but we tend to use properties.
But not just the contaminants. I was thinking that if you point the instrument at a star-forming galaxy, for instance, you might be able to find H2 regions, right, with strong O3 emission and do the same kind of analysis that you do.
Yes, that's also is possible to do. Like, for example, there is a work for Andromeda galaxy where they also study H2 region. The truth is that I think so now the planetary nebula spectrograph has a third arm, which is an H alpha camera, because combining the O3 and the H alpha, you have even more information also to study H2 regions. So it's possible to do this type of studies.
Cool, thanks.
Okay, thank you. So we don't have a discussion session this morning, but we can have questions during the afternoon. So if there are further questions for Ariana, and also I liked your suggestion of fitting dark matter profiles into this system. So that's interesting to discuss. So anyway, further discussions we can carry out at 4:30 in the afternoon. So let's continue with the program with Eduardo Cipriano. So Eduardo Cipriano from the IAG USP will be speaking about measuring the amplitude of dark matter fluctuations with JPAS galaxy clusters. Okay, I don't see Eduardo online. Okay, let's give a couple of minutes to see what's going on, and then we can continue with questions to Ariana then.
Hello, my name is Lucas, and just two questions. The data used in your search, where there is one observatory only, or it's a lot of bays that you use?
Yes, that's a very good question. So I'm sorry. Is that done as a WHT telescope in La Palma? So the instrument is there in La Palma.
Okay, and other thing is the next generation of large telescope will help your search, or they don't interfere directly in your search, the data in your search?
So That's something that I have to think of. Actually, I was thinking about this after Amanda's question, because it's true that now the new generation of instrument allow you to see further away, maybe even planetary nebulae.
Yeah.
Of course, this is a very specific instrument. There have been thought of moving it to Chile. So the WHT is a 4-meter telescope, so it could be mounted on a larger telescope, so a larger mirror, so maybe to have to be able to see even further away. So that's possibility, but I don't know, because the ISO standards are extremely neat, so it's very hard to put an instrument which is not done within ISO standard into a telescope. And yes, but that's an interesting, very interesting point. Yeah.
Thank you.
Okay, so my mistake, actually, I was looking at an older version of the program. Now we have Marco Rossi about dark matter in dwarf galaxies. And then we have Eduardo Cipriano. So, you prefer this microphone or this one?
Hello? No, let me see. Usually I get some problems with this one. Okay. Yeah, okay. So, hello, everybody. Let me check. So, my name is Marco Rossi. I work at the Observatory of Valongo. And I'm going to talk a little bit about dark matter in dwarf galaxies. And this work is to be done in collaboration with Raimundo Ferreira Filho, Ariana Cortesi, Carmen Destelbestre, Sione Gonçalves, Tiago Sione Gonçalves, everybody at Observatorio do Valongo. Okay, so the outline of the talk. I'm going to try to give a brief review of what do we know about the dark matter in dwarf galaxies. First, I'd like to speak a little bit about the general properties of dwarfs. Then, what do we know? What is the dark matter content of dwarf galaxies and how it varies with different types of galaxies? Then I'm going to talk a little bit about the density profiles of dark matters and some issues related to the value of the central density in these galaxies. Initially, it's called the cusp profiles versus core profile. And then a little bit about what are the most recent results about search for dark matter in dwarf galaxies through signals of high gamma ray emission. And lastly, I'll give a little bit an overview of the ongoing projects that we're doing that are mostly related to dark matter with dwarf galaxies. I have to disclaimer, I mostly work with baryonic matter, so this is our new projects, and so they are very. I'm going to go just a very introduction about this ongoing projects. Okay, so let's start with the dwarf galaxies. So studies of the luminosity function of galaxies in the local universe and in cluster environments show that dwarf galaxies in general are the most abundant objects in the universe. So and when we talk about dwarfs, one thing that is important to say, we mean objects that are at least 1 order of magnitude less luminous than the Milky Way. So dwarf galaxies are very numerous, very abundant in the universe. According to these standard cosmological models, galaxies form in the scenario that is called bottom-up. Therefore, small galaxies form first, and then through mergers of smaller galaxies, we can form more massive systems. Therefore, dwarf galaxies are very important, very interesting objects to study to understand how galaxy forms and how galaxy evolve. Lastly, it is well known that dwarf galaxies tend to be dark matter dominated, so we have a large number of objects very nearby as well, where we can investigate and study the nature and properties of dark matter. What kind of dwarf galaxies do we know? Usually, dwarf galaxies are divided like the most massive system in two types: the passive ones and the gas-rich ones. Among the passive dwarfs, that are basically dominated by all-star populations and they are gas poor. There are three main types called dwarf ellipticals, dwarf spheroidals, ultra-faint dwarfs. The main difference is between these three types is related to luminosity. And so the faintest one are called the ultra-faint dwarfs, which are a fairly recent type of dwarfs that have been discovered after the SDSS survey. These ultra-faint dwarfs, they are very faint. I mean, their luminosity are less than 10 to the 5 solar luminosity. And for this reason, usually they are mostly found in the halo of the Milky Way. They can be observed only in the halo of the Milky Way. On the other hand, we have healthy dwarf galaxies that are gas-rich. They have young stellar populations. They form stars. And they are called dwarf irregulars, although there are some kind of sub-classification that it's not important to get into these details right now. We know that the environment plays an important role in the properties of galaxies, and this also applies to dwarf galaxies. And in the local group, for example, we find a very clear separation between the location of different types of dwarf galaxies. So in general, the passive galaxies, the dwarf spheroids, dwarf ellipticals, or ultra-faint, are found within 400 kiloparsec, within 400 kiloparsec of the most massive members, which are Milky Way, Andromeda. And here you have an example of the Andromeda system and its system of satellites. So in the Milky Way, there are roughly 100 dwarf galaxies in the Milky Way, sorry, in the local group within 1 megaparsec. In order to estimate their masses, we need a tracer, a dynamic tracer, a kinematic tracer. Usually, we can use stellar or gas kinematics according to the type of galaxy. If the galaxy is gas-rich, we use gas. If it's gas-poor, we need to use the movement of stars. And then we can determine the total dynamical mass through this formula. So we need to define the radius of the galaxy and the velocity dispersion of the stars or the gas. And then we can derive the dynamical mass. Here, when we deal with dwarf spheroidal, it's usually common to define the dynamical mass in this way when it is calculated at half the light radius in the 2D projection of the image. So as you can see from this plot, once we compare the dynamical mass and the luminosity of dwarf galaxies, and we trace these lines that defines the continuous value of the mass to light ratio, we can see that there is a very great variation of the mass to light ratios from dwarf galaxies where the mass to light ratio is 10 to dwarf galaxies where the mass ratio is above 1,000. So there are a large population of very faint systems that are very dark matter dominated compared to the brightest one. To give you an example, this is the dynamical mass versus radius of dwarf spheroidals. This is Draco dwarf spheroidals, 76 kiloparsecs, the satellite of the Milky Way. So as you can see, the dynamical mass, so the dark matter is basically dominating the whole profile at every radius. So, because here you have the comparison between the stellar mass and then the dynamical mass. So at half-light radius, there's roughly a factor of 100. So this plot, just to give you an idea of how dark matter is important in the dynamics, in the kinematics of these galaxies. Doing this kind of measurements, let's say dynamical mass, kinematics of stars, is more complicated when we deal with ultra-faint dwarfs. This is an example of ultra-faint dwarfs. In these objects, you have only a handful of stars that belong to the galaxy. Here you have the green dots. They basically are stars that have been spectroscopically identified as members of this galaxy. So it's difficult to define a radius, and then it's difficult to define a mass profile when you have only 10, 20 stars. But in general, these works try to follow up spectroscopically all the candidates in the galaxy and try to find the ones that have a similar kinematic, similar velocity that can be associated to the same system. And that's why in these objects, in general, so the faintest ones are characterized by very high mass-to-light ratios, so they are very dark matter dominated, but also the uncertainties are very large. So we've seen that there is a class of dwarf galaxies that are very dark matter dominated, but on the other hand, there are evidences of very few examples of galaxies, of dwarf galaxies that are dark matter deficient. In 2018, it came out this paper about an object that is called NGC 1052 DF2, which is a type of dwarf galaxies that is defined as ultra diffuse galaxy. Basically, they have properties that are similar to dwarfs, like surface brightness, total mass, but they are much more extended, much more diffuse compared to typical dwarf spheroidal galaxy. But also they are gas poor and dominated by all stars. So since this galaxy is pretty far away, 20 megaparsec compared to the local group, the only way to do kinematic studies is by tracing the brightest systems in this object, which are the globular clusters. So, but in these cases, the only way to get an estimate of the mass, one need to go after the globular cluster systems in these galaxies. And the outcome of this work basically is that the dynamical mass, the black curve, and the baryonic mass, the orange curve, are comparable, so that the difference between these two values is very small, very tiny. So there is not much space for dark matter in this object. This result was a bit controversial. There are several other studies that try to investigate this object. Some claims that the distance is wrong, so a closer distance and a different dynamical models could resolve this issue and provide dark matter to baryonic matter ratios of about 50, at least 15, so that's more or less reasonable for dwarf galaxies. But the issue is still open with this type of systems. Always on this trend of dark matter deficient galaxies, another study with different type of objects, in this case gas-rich objects, dwarf irregulars, has found that there is a class of dwarf galaxies that have gas, so it's easier to estimate the dynamic mass. But when they're compared to the average type of dwarf galaxy in the sample, the dynamic mass and baryonic mass are very small compared to the typical value of the sample. That is, the ratio is about 10. So for a normal dwarf irregular galaxy, dynamical mass of a baryonic mass of 10 is the average, is what is usually found. Well, these objects are, as you can see, fall below this line, which defines a ratio of 2. So there are different type of system, different type of dwarfs that are also giving evidence of, let's say, deficiency of dark matter, which is a puzzle for models of structure formations that need to be addressed. So let's move to the density profile of dark matter. The rotation curves are one of the best tool to determine the distribution of matter in a galaxy. A rotation curve is a plot like this, where you have the velocity as a function of radius along the traced along the semi-major axis of the galaxy. And when usually as a tracer, when we do this kind of studies, we use atomic hydrogen, because it is the component of interstellar media that is most extended. So it allows to trace the outer until the other parts of the galaxy beyond the stellar disk. And this type of diagrams compare the main components that we have in a galaxy. So the stars, gas, and dark matter halo, and try to fit the observed velocity curve. The density of the dark matter halo, according to cold dark matter simulations, pure cold dark matter simulation, provide that find that the typical density of a dark matter halo is described by the Frank Navarro white profile, and this is a universal profile that applies to all galactic scale and also to cluster of galaxies. The profile goes as for smaller radii, this goes as 1 over r, and at larger radii it goes as 1 over r to the 3. So at the center there is a kind of divergence as the distance gets closer to the center of the galaxy, and this trend of the profile is called a cusp. So in this case, as you can see, a Navarro-Frank white profile is not able to correctly fit the velocity curve of the galaxy, especially in the central part of the galaxy. In order to solve this problem, other profiles have been introduced, the so-called chord density profiles. An example is the very used profile is called the Barkert profile. As you can see in the center, the density is constant, so you don't have anymore this issue of increasingly fast density as you at a lower distance, smaller distances from the center. In these cases, comparison between Navarro-Frank white and Barkert model show that the density profile with a core is better able to adjust to fit the velocity curve of these dwarf galaxies. It's important, we can do this kind of studies only in dwarf galaxies because dwarf galaxies don't have bulges. In a spiral galaxy like the Milky Way, the bulge is the main component, the main dynamical component. So we cannot, so the baryonic mass is dominant in the center of a spiral galaxy. So we cannot trace, we cannot determine what is the central value of this profile in a massive spiral galaxies or in a lenticular galaxy. So that's why it's important to use dwarf to do this kind of studies and constrain the value of the density in the center. As you can see, most of the dwarf galaxies that have velocity curves traced by the H1, by the atomic hydrogen, do prefer to chord density halos compared to Navarro-Frank white halos. Here you have the value of alpha as a function of radius. So there have been a few efforts, a few attempts to try to sort out this issue, and the three most favored scenarios are listed here. So the one issue is that the baryonic matter actually do affect the distribution of dark mass due to star formation and the feedback effects that can alter the distribution of dark matter because of explosion of supernova and ejection of gas from the central part of the galaxy. Another, for those who are most attached to the Navarro-Frank white profile, so the issue was pointed in the way these velocity curves are analyzed and treated, because usually when we do when we do the analysis of rotation curve, we assume that the gas is rotating in a circle around the center, but this is not necessarily the case, because you can have gas outflows and gas inflow. The galaxies accrete gas that may differ from circular motion assumption, therefore affecting the interpretation of the result. Finally, we can have also an exotic alternative, more exotic alternative, changing the characteristics of dark matter particles, the so-called self-interacting dark matter. There's a question mark, I don't know why, maybe because I don't know what it is exactly. But basically we have the current model of dark matter is that dark matter particles only interact weakly. And when they interact, they annihilate. In the case of self-interacting dark matter can also elastic scatter between themselves, and in this way exchange energy. And in the central part of the galaxy, being denser, the distribution of density can be affected by this interaction and changes by the interaction between the particles, the dark matter particles. Actually, the first option, the first interpretation, is the one that is most accepted, because we know that dwarf galaxies, galaxies in general, they form stars, and we see the outflows that are associated to starburst and star-forming events. So the effects of the outflows, if this the ejection of matter is at sufficient speed, it can change and affect also dark matter. To make this a bit clear, there's this cartoon that I find very, very clear to explain what happens in this case. So we have dark matter here and baryonic matter here, gas that is forming stars, and we have a starburst. So there's an explosion. Matter is ejected from outwards from the center. So the gravitational well at the center varies, is lower because of the loss of matter, and therefore the attraction force on the particular matter is reduced because of the different content of matter. If and it moves away. If the matter falls back to the center, since the dark matter is more distant now, the dark matter particle, so the gravitational force is lower compared to the beginning, and therefore there's not enough to bring it back to the central part of the galaxy. If we have different episodes of formation, so this event is repeated, and the neat effect is to modify a cusp with a core. Simulations also do find this kind of relation, and what is the current paradigm is that in general, when dwarf galaxies are star forming, they do show core. When they are passive and not star forming, they do show cusp profile, because the star forming events, the feedback from star formation is not sufficient to make this change in the central density of the galaxy. In this plot, you have stellar mass versus the exponential of the central part of the density profile. The red crosses are simulations, the blue dots, the blue squares are the observations. And as you can see, there is a threshold stellar mass where one can see the beginning of this change in the profile. Okay, this is a similar thing. Okay. Let's go to the third part. So we know about the we have a hint of the distribution of dark matter in galaxies through the velocity curves. We know that dark matter, dwarf galaxies are very dark matter dominated, especially dwarf spheroidals and ultra-faint dwarfs. So we have excellent targets to search for evidence of dark matter through the decay products of the dark matter particles in the central part of the galaxy or in the halo. The current color matter scenario predicts as a most favored candidate a so-called WIMP, weakly interacting massive particle. Its mass it ranges between 10 times the mass of a proton to 100,000 times the mass of a proton, so 10 GeV to 100 TeV, according to the standard models. According to supersymmetric model, this particle, as it interacts with this antiparticle in the central part of the galaxy or in the halo of dark matter, they can produce normal particle, quarks or leptons, that then can shower and produce high energy photons, gamma ray photons. So there is a huge effort with gamma ray telescopes from space and from the ground to look for these signals, not only in the central part of the galaxy, but also in dwarf galaxies, because they have an additional advantage, especially dwarf spheroidals. They are close, they are dark matter dominated, and they are gas and gas-free, gas poor, and also a low star content, because in this case, it is also difficult to find the signal because of contamination from diffuse sources, cosmic rays, high energy cosmic rays interacting with the gas in this interstellar medium, for example, in our galaxy, or point sources like pulsars that shows to be emitters of high energy particles, gamma rays, and also positrons and electrons of high energy. So again, dwarf galaxies are perfect for studying dark matter. What happens here? So as I was mentioning before, we have a WIMP. These are very massive particles, at least 10 times the proton mass. It interacts with its antiparticle, collides with antiparticles, it annihilates, and something happens. So there are several channels that are predicted by particle physics according to the supersymmetric models that can produce different outcome particles, quarks, tau leptons, or bosons. The main channel, as you can see here, the main favorite channel is the one that produce quarks and tau leptons, producing the higher energy flux. In this case, the flux is calculated for the typical mass of a WIMP of 100 GeV. So you probably have seen this kind of formula. This is the typical way to represent what happens and what is the signal that one would expect. So here you have the measured flux, the expected flux from the gamma range. You have a part of the formula that's related to particle physics and a particle that is related to dark matter distribution. So here you have the annihilation cross-section of the particle-antiparticle, of the WIMP particle-antiparticle, which is the parameter that is constrained by these observations. Here you have the different products, and these are also predicted by particle physics. Remember, the N over the E is this kind of particles that are produced, quarks or lepton or bosons. Every channel has a different ratio that is represented by this parameter B. And then it enters the density of the dark matter. So the dark matter distribution is calculated through this formula here. This parameter is called the J factor. That is strictly related to the density of dark matter in the source, average over the angular size of the source. So if you look at the literature, the last 15 years, there are lots of works about search for gamma ray signals or other high energy particle signals. But unfortunately, in the case of gamma rays, there are no results so far. There are always non-detection and an additional effort to put upper limits on the parameter that defines the annihilation process of the particle of the WIMPs. I just wanted to show two examples. The segue, the search for a gamma ray emission with Fermi and Magic Telescope within this range of energies. Segue is one of the famous ultra faint dwarfs in the Milky Way, very dark matter dominated, mass to light ratio of 2000. As you can see, there's no clear, this is the position of the galaxy, and the signal is basically noise fluctuations. A most recent work that tried to combines all the gamma ray facilities that we have at hand, basically Fermi Space Telescope, and then all these are ground space telescopes scattered between Arizona, South Africa, Canary Islands, and that's it. So they did an estimate of the two main channels, quark channel and electronic channels, and they combine all the different instruments. And this curves basically define the upper limits of the cross-section, the parameter that defines the annihilation process, and the combination of the 5 instruments. Here you have Fermi that has the larger extent, especially low energies, for both channels. So this is although it's written preliminary, is the most complete review and update of the cross-section limits of these two channels for gamma ray observations. Okay, so this was an effort to give a quick review of there are many more issues related to dark matter and dwarfs, and to the testing lambda CDM with at small scales, but I don't have time to go through all of this. So let's talk a little bit about these 2 ongoing projects that we are carrying out that are related to trying to relate to dark matter and in dwarf galaxies. So the first one is to try to address the relation between globular clusters and dark matter halo in dwarf irregular galaxies. And the second one is to try to address what is the typical dark matter value of groups of dwarf galaxies, and how does hierarchical clustering works at low masses. Okay, so globular clusters. There is a very well-known relation about halo mass and globular cluster mass. So that if we count all the elements around the galaxy and we determine the total mass. So for massive galaxies, it is very well known since 2009, I guess, that there is a linear relation between dark matter and the mass of cluster. So this relation in a way is a bit counterintuitive, because it assumes that globular clusters, the globular clusters are the first structures, stellar structures that are formed in a galaxy. And the fact that there is this correlation means that their formation is also related to the formation of the halo that hosts the galaxy. But we know that massive galaxies are the result of a merger of halos. So in this way, it's not very clear how this correspondence can be maintained even after the different process of mergers that occur in massive galaxies. But when we move to low mass galaxies, low mass halos, well, the first study that tried to enlarge this relation was done by Forbes and collaborators, using mostly galaxies in the local group. And as you can see here, the outcome of this study is that the relation is maintained even at low masses, and in this linear correlation that is found at higher masses. But the issue of this work is that if we compare this with models from CDM simulations, the relation should have a turnover at a certain mass. Also because this is what happened when we plot stellar mass versus halo mass function. So in a way, the stellar mass should follow the same trend that the galactic cluster, the global cluster should follow. So starting from this issue, from this question, what happens at low masses in this relation, and how can we keep investigating this relation? We decided to select a sample of dwarf irregular galaxies with low halo masses to try to feel this region. This work was mostly done with dwarf spheroidals. Dwarf spheroidals are, because of the lack of gas, it's more complicated to determine, to properly assess the dark matter halo. So dwarf irregulars, because they're gas rich, they have the advantage of making it simple, making it easier to estimate the mass halo. The local group galaxies are also affected by the interactions with the most massive members. So this can affect the number of global clusters in small galaxy. So the idea was to select a sample of pretty isolated, near isolated galaxies, okay, gas rich, and go through, try to determine this relation. Of course, looking for global clusters in dwarf galaxies is much more difficult because the number of global clusters decreases with stellar masses. At very low, at 10 to the 7 stellar masses, probably the galaxies probably do not have lost any more global clusters. The contamination effects are more important, and so there are some issues related to the search for global clusters in low mass galaxies. So we, just as I was mentioning before, so this project is led by Raimundo Ferreira Filho, which is a graduate student at Palongo. And so as I was saying, we started from a sample of dwarf irregulars. You have a couple of galaxies shown here. They were taken from another survey that is called made by Spitzer, the S4G survey. And we combine the optical images from the Delve survey with H1 information that comes either from single dish observations, and for some of them we have also H1 maps. So in this case, we will be able to constrain even better the halo mass of these galaxies and relate them to the position and distribution of clusters. The range of masses that we are sampling so far, it's so the radical mass down to 8.5, and stellar mass between 8 and 9, roughly. The main objective, so it's okay, define this relation dwarf irregulars and search for GCs, study the property of GCs, and see if they also hosted by model population as is found in more massive galaxies. The selection is done with purpose extractor. So we define the photometry and we separate extended sources from point sources. 4 bands, GRIZ. Then we apply color selection cuts based on simple stellar population models, assuming that the typical age of global clusters is between 6 and 13 gigayears and very low metallicity. We only include the selection above 5 sigma. And then we, for these two galaxies here, we have estimated, actually Raimundo estimated the number of galaxies and the total mass, the number of global clusters and the total mass associated with them. This is a very preliminary result. We still need to tune our technique to check the contamination. But I mean, so far, we are not too far from what is found with the other systems. How much time is it? 2 minutes, okay. The second project is related to dark matter is, okay, we know that our close groups of our close group of dwarf galaxies is represented by the Magellanic Clouds. So the large Magellanic Clouds and the small Magellanic Clouds, in fact, they are not just a pair of dwarfs, but it seems that they form there's a small group of dwarfs that has been accreted by the halo of the Milky Way. So this is seems to be corroborated by the fact that the new ultra faint dwarfs that are close in position to the two systems, the two main galaxies, seems to be associated to them. It's very what we know about small groups of galaxies is very little. It is important to investigate what happens, what is the clustering of this kind of galaxies. It is from the CDM models. It is expected that a galaxy like the LMC should have at least one massive satellite and 5 to 40 smaller ones, with 1,000 times its mass. So it's also important to look for dwarf groups, because they also seem to be related to another issue that is related to dwarf satellites, which is the apparent distribution in the main galaxies in the local group, like Andromeda, Milky Way, or Centauri, that this satellite seems to be oriented in a preferred direction, a preferred plane, instead of being uniformly distributed, which is what is expected by CMDM models. So, and one explanation could be that these groups have been accreted by the galaxies, the main galaxy. So there are only very few studies about groups. So the idea is to look for a region of the sky that is the catalog of groups with spectroscopics, when we can do this kind of selection. So the approach is to select in this group of catalog group galaxies with magnitudes fainter than the typical magnitude of the LMC, and we ended up with 35 candidates that could be in principle small groups of dwarf galaxies, and they need to be further investigated. We need to estimate the total mass and the dark matter mass in order to find out if they can be visualized groups or not. So it's important to know the next step. Now we have selected the groups. Now we need to calculate all parameters: stellar mass, dynamical mass, and distances between sizes of the group, and determine what is the dark matter content of the systems. Okay, the summary. Dwarf galaxies have a wide range of dark matter content. They have a useful tool to test lambda CDM prediction. There are, despite the success of lambda CDM, there are still some issues at small scales that are related to dwarf galaxies, and so it's important to use dwarf galaxies to test the model. So far, there is no results on the evidence of the wind annihilation from dwarf satellites of the Milky Way. Thank you.
Thank you. We have time for a couple of questions. So are there questions here from the, yes?
Oh, hi, Marco. So you mentioned a bit the Van Dokkum galaxy, which has no dark matter. And after that claim, you know, there were rebuttals, and then people found other galaxies, and now it's more or less accepted, I think. But can you comment a bit more on the status of this and which classes of galaxies now have been confirmed to have been detected? And what's your opinion on this?
So far, I've only seen two galaxies, two ultra faint dwarf galaxies. They are all in the same system, I think. And but I didn't follow too much the recent studies. I've seen that the distance of the object is the main issue, and there is a very recent study using 40 orbits of the HST that places the galaxy even farther than this. Therefore, the distance seems pretty solid, and the distance is the main problem in discriminating the scenario of the dark matter deficient or not. So so far it seems that this object is definitely dark matter deficient. And compared to this, there is also these are the study related to completely different objects. So they are gas rich, and they also show this similar deficiency in dark matter. So
I think there were other galaxies found not in the same group, but not by Van Dokkum. And anyway, I think this. What's your opinion? I think this, from what I understand, this kind of confirms that the cold dark matter scenario, or not, right? That it should be a few objects that would have almost none.
Do the cold dark matter scenario accept this? No, I don't know. To be honest, I don't know this. But I think that there are efforts to try to explain this through feedback, the ejection of matter, ejection of that, because tidal interaction could be also a way to reduce dark matter content of galaxy. But these galaxies do not seem to have tidal features. One interpretation could be in this scenario there is a possibility of forming a galaxy with other matter. It's called the tidal dwarf galaxies, but they originate from interaction of massive systems. So you need to have two massive systems and gas that is disrupted and collapsed to form objects with other matter. So in this case, it is possible to form. There are examples of dwarf galaxies with other matter. How long these objects can survive, it's still a matter of fact. But maybe it could be the link between these kind of objects and the tidal dwarf that actually are diversion, gas rich, and start forming of the systems. But I mean, the details of the scenarios that do lead to this kind of objects are, to be honest, I don't know.
Okay, thanks.
Thiago has a question online.
Hi, Michael. Great talk, and it's always very interesting stuff. I hadn't seen those plots yet, so referring to your project one that you referred to, the one with Raimundo, I have two quick questions. One, you plot the dynamical mass as a function of stellar mass, I think, and I assume the dynamical mass comes from the single dish data.
In this case, yes, it is.
Yeah, that just to make sure. And the second question is, do you plan to do some sort of similar game? Do you have enough globular clusters in these galaxies that you can do something similar to what Peter Van Dokkum is doing for the ultra-faint dwarfs, that you can probe also the dark matter profile in a way with the globular clusters?
Well, spectroscopic follow-up is essential just to test that we are doing things correctly.
Yeah, so, that's a good prediction.
Once we get spectroscopic follow-ups, we can do this, but we can compare. Actually, the idea was to use ATCA, is to do this without having we are needing to do spectroscopy with the global clusters, because we can trace the variation of the gravitational potential and the dark matter distribution through the rotation curve. But definitely it's essential. I mean, next step, once we define all the candidates, it's essential to do spectroscopy follow-up, and then we can do the same thing as Van Dokkum.
Okay, cool, thanks.
Okay, I have a lot of questions, but let's take the last question from Karim. And just to say that today, in the morning, we don't have a discussion session, but at the beginning of the closing session, we can take further questions, maybe separate some minutes and take further questions for all the speakers of the day. So let's get the last one from Karim, and we can continue at the end of the day.
Thank you. Very nice talk, Michael. My question will not mention Van Dokkum that everybody's mentioning right now. It's about the COSPI course. I think it was perhaps the second one that you were mentioning. You mentioned how as one of the arguments for basically not having a good handle between COSPI versus court dwarfs was some challenges in understanding rotation curves when you consider deviations from simply rotation. I'm thinking, so this is only for dwarfs, I imagine, because this is where we see this issue. I'm thinking of what kind of non-rotation. I mean, we don't really see bars. I'm trying to understand what kind of structure and at what scale.
Inflow of gas, for example, or outflows of gas. These are the main issue that they can change the circular approximation of velocity in the gas.
So it would not only be in the central, because I was thinking how to have a good handle on nonlinear motions. How are they actually reflected in the rotation curve? I guess I don't know enough about this. I was wondering at what scales in the rotation curve, in what region, and how you get a handle on those.
In this case, it must be in the center, because the issue is in the central part of the galaxy. And when you have the inflow of gas, you can have it in the outskirts or in the center. It depends. I mean, not necessarily one way, a certain direction. But in the literature, I mean, what they mention when they try to, as a counter argument to those people that argue that the chord halo was not necessary, is the fact that you can have these two options that affect the assumption of circular velocity.
And can you use globular clusters to trace those inside regions? I wonder how to trace the dark matter halo.
Usually in the center you have a smaller number of globular clusters. So I don't think usually when they do this kind of dynamical models with globular clusters, they start from a few kiloparsecs and beyond. So I don't think you can do this with globular clusters. And in the central part, especially with star forming systems, the contamination from star forming region is more difficult to discriminate between globular clusters and normal star clusters. So it's more complicated.
Yeah, good, thank you.
All right, so now we proceed with the next talk from Eduardo Cipriano of IAG USP on measuring the amplitude of the dark matter fluctuations using JPass clusters. And Eduardo, I'll let you know when you have 5 minutes left. We cannot hear you. I don't think you're muted, but we cannot hear you. No, zero sounds. There is an option. Maybe your Zoom is trying to get the sound from a headset and you don't have a headset. So there is an option on Zoom when you go to the main bar in the audio options, I believe. No, well, audio settings, you can choose the source of your microphone if needed be. It won't work here because we are not using the audio. Zero sound. I don't know if you try this, but if you, on the audio part of the Zoom, no, you have you have a little arrow where you can choose the source of the sound. I guess it's trying, yeah, oh, it's very, very dim, but we heard something. Okay, now we lost it. Okay, let's wait a couple of seconds. Otherwise, we can continue the questions to Marco. We hear you, but very, very, very mildly. Yes. Try again. Yeah, a little bit louder if you can. No, worse. The other way, before it was better. No. Do you want perhaps to try with a headset to see if the microphone works better? Are you using like a built-in microphone? Yes. Now we hear some sound. Can you hear us? Agora não sei se ele ouve a gente. Can you hear us, Eduardo?
Martim? Alô?
Agora te ouvimos perfeito. Agora te ouvimos perfeito.
Mas eu não te ouço. Tá, só para ver. Quanto tempo eu tenho para falar?
Você tem 40 minutos para falar. Quando saltarem 5. Ou seja, quando passarem 35, eu te aviso.
Ok. Obrigado.
Você tem 40 para apresentar e 5. A gente agora é perfeito. Não sei o que você fez.
Por alguma, eu saí e entrei, mas por alguma razão eu não estou ouvindo nada daí. Tá?
Tá.
Então, depois das perguntas, você me faz pelo celular aqui. Tá, desculpem todos. Vamos começar aqui, tá? Bom, desculpem o inconveniente. Curiosamente, agora eu não ouço vocês, mas vamos lá. Qualquer coisa, o Martim passa pelo celular. Então, a ideia desse trabalho aqui é falar sobre o que nós estamos fazendo no projeto JPAS relacionado com a matéria escura, né, que é a medida da amplitude das flutuações de matéria no universo, né? Bom, usando aglomerados de galáxias. Aglomerados de galáxias são fundamentais na história da matéria escura. Começa que a própria matéria escura foi descoberta em aglomerados de galáxias na década de 30, quase 100 anos atrás. Desde então, várias descobertas, várias determinações de parâmetros relacionados com a matéria escura vêm de aglomerados. Tá? Por exemplo, do que eu vou falar aqui, a amplitude do espectro de potência da matéria, né, que tem a ver com as flutuações. Bom, eu estava falando sem compartilhar. Agora eu estou compartilhando. Se alguém puder me dizer se está funcionando.
Está funcionando.
Bom, eu vou supor que está funcionando. Se não estiver, alguém me mande uma mensagem, tá? Então, eu estava falando que os aglomerados de galáxias, eles, desde 1933, estão sendo usados para determinar parâmetros em cosmologias associados com a matéria escura, né? No caso, Ok, obrigado, Martim. No caso, eu estou falando aqui da amplitude, ok? No caso da amplitude de flutuações da matéria escura, né? Já foi, por exemplo, usado muito para determinação de ômega da matéria e vai ser usado, né, a partir de agora também para determinação de parâmetros associados com energia escura. Tá? Qual que é o básico da ideia do uso de contagens de aglomerados, aqui o número de aglomerados, tá, em função do observável, né, o mínimo e o redshift, ele tem a ver com a cosmologia através do volume, que a gente está mostrando do universo, mas que é uma componente subdominante, e principalmente esse dN/dm, que é a função de massa das estruturas do universo, tá? Associado com o espectro de potência. Contagens de aglomerados, basicamente, eles conseguem colocar vínculos nesse parâmetro sigma-8, ou sigma-8 times, sorry about that, guys. So, I was kind of confused. So, galaxy cluster counts constrains this combination of parameters. Sigma-8, which is the normalization of the matter power spectrum, which is related to the amplitude of fluctuations on a scale of 8 megaparsecs, times omega matter to the power of Q, where Q is approximately 0.5. So you can see in this plot the kind of contours, the degeneracy between omega matter and sigma-8 from galaxy cluster count studies. So we can see that we can actually constrain is this combination S8. So, and the other part that I didn't mention of the equation is the mass observable relation, which is the P of X, where X is the observable, given the mass and the redshift. So there are several observables we can use for galaxy clusters. For optical surveys, it could be richness, luminosity, stellar mass. In microwave surveys, the Y-Compton parameter from the Sunyaev-Zadovich effect, and which has been used several times in X-rays, X-ray luminosity, temperature, and even the product between, well, an equivalent of the Compton parameter YX. So, but what I'm going to talk here is what we can do with JPass to contribute in this field in the light of the other surveys that happened and the other ones which will happen. So what's the space we can occupy? So for those who doesn't know, JPass survey, the survey I'm part of, is a large area survey, several thousand, it's 8,000 square degrees, which will be done with a 2.5 meter telescope, which is located in continental Spain, with the differential of a system of 55 narrow band filters, which you can see here, which are designed to be able as a powerful photometric redshift machine. So we had a talk about photometric redshifts. So this is a photometric system designed to be the most efficient possible for photometric redshifts, which are supposed to, and we have already proved in a mini JPass survey that we can have photometric redshifts which are 10 times better than those from 5 filter surveys, typical U, G, R, I, and zeta images like Sloan and ES and LFST, etc. Those can be deeper, but so can reach galaxies further away. But the precision of the photometric redshifts, what we're going to get from JPass will be 10 times better than those surveys because of the resolution in which we are going to sample the spectrum. So JPass is here in this plot that compare area and depth of surveys. So we see that it's a large area survey, but it's rather shallow compared to even DES and Punstar and others, nothing compared to LSST, for instance, or ST deep. Okay, it's shallow. So what can we do in this area with JPEGs? So cluster counts, as I said, considering the normalization of the power spectrum. So sigma 11 is sigma 8, considering the H naught of 70. So the limit on the precision that we can find sigma 11 has to do with the number of clusters we are going to find, the more the better, and how well we can measure the masses. But we see that even for moderate sized samples, this term, which is related to the Poisson plus the intrinsic fluctuations of the number counts of clusters in the universe, is completely subdominant. We are dominated by the uncertainty on the mass scale of clusters. So that's what we have to see, so we know how well a survey would perform. So in mini-JPEGs, we are going to use stacked weak lensing to calibrate the mass scale of clusters. So how well can we do that? So to know that, we are using this simplified formula from Weinberg, 2013, that relates the precision of that with the number of the mass, with the number of clusters, the ellipticity of the sources, the mass of the clusters, the density of background sources, and a geometrical term. Okay, so we are going to test two cases, one with masses larger than 1.10 to the 14 solar masses, and another one with masses higher than 10 times to the 13, deep in the group range. So in the mini-JPEGs, we found that for our sample, the ellipticity, the intrinsic ellipticity of galaxies, which is the main source of noise in weak length studies, is about 0.23, because it's a shallow sample. We have number density of galaxies as a function of redshift. So the overall density of background sources is 2 galaxies per arc minute square, which is not great, and falls to 1 by redshift 0.14. And this is the geometrical term, which is has to do with the efficiency of lensing, supposing an SIS profile. Here, I try to do something to avoid the unrealistic excess of probability the SIS profile generates on lower redshifts. This is the expected number counts given a typical cosmology. So this is 10 times to the 14. This is 5 times 10 to the 13 in beams of 0.15 in redshift. So crunching all those numbers, what we get for the precision, the uncertainty of the mass scale in percent is here. We can get below 5% in this redshift, this low redshift range here. So when we go from 0.35 to 0.4, the error starts shooting because of the low number density of background galaxies. And also we can see that we don't gain a lot by using the groups, the objects lower than 10 times to the 14, because they are much more numerous and increases this, but the mass is lower, and the inclination of the mass function at this point is kind of flat, so it doesn't compensate. Or on the other hand, it barely compensates. So there's not a lot of gain in going for the group range. And well, supposing we can get 2 or 3 redshift beams, which means that we can have uncertainties of the order of 3% or 4, and which translates in sigma 8 of 2 to 1.5%. So this is the statistical error we are going to have in a survey such as JPEGs. So, but why to do that? By the time when JPEG reaches full area, we have a lot of other surveys like KIDS, DS, HSC, which are going to be completed, and Euclid and LSST would be ongoing. So why to do that? Well, we are facing now some of attention in this area. It's similar to the Hubble tension, but it is called the S8 tension, which is the difference between measurements from the CMB, and the sigma 8 from CMB is quite a direct measurement. Differently from H0, it's kind of indirect, and several other probes of the dark matter fluctuations from local measurements, and including here on the bottom cluster counts from SPT and for DES year 1. So we have this tension. It's not as strong as the Hubble tension because the error bars are much larger, but still we have this hint of attention. And in this tension, as in the Hubble tension, the question is this a real tension, something wrong with the cosmological model, or systematics are driving our results wrong? So, and that's in this part where JPEG can have a space in here. So this is the size of a typical error bars that only JPEG cluster counts only will have, following the previous slides. And we see that's competitive, but I will show in the end of this talk that we expect to keep systematic errors below that, and therefore it will be able to make an important contribution for the discussion. So for detailing all of that, I'm going to go through all the steps towards making cosmology with cluster counts, what we are doing in JPEG, and the people which are involved in that on the São Paulo group here. So we are going to use weak gravitational lensing. So this is the deformation of the shape of background galaxies due to the gravitational fields of clusters of galaxies, which induces a signal like we see here. We have random shapes here, and we have a small alignment due to the gravitational lensing effect. These have been measured for the last 20 years. This is a plot from my thesis, my PhD thesis, showing the pattern that the ellipses of background galaxies do around massive clusters. So we want to measure the tangential shear. From the tangential shear, as we see in this equation here, the tangential shear times the critical lensing density, which depends on the geometry, on the distance between the lens and the source. We get the density contrast here, okay? And we can model that with an FW profile or any other profiles, and we can get masses from these objects. And in particular, for surveys where the density of background galaxies is low, we cannot do that cluster by cluster, but we do stacking. We use several clusters together, and we get a very nice signal to noise. And as well, we average out several effects like a triaxiality of galaxy clusters, the influence of background and foreground structures, the presence of substructures in clusters, etc. It all averages out once you have enough clusters in a stack. So André Vitorelli did his PhD with me, and now he's in JPL working with DWST data. And he's someone which is in charge of the calibration of the mass observable relation, which is this part here of the equation we have to solve. So we have done that. So he developed a code for stacking, for his thesis, for the mass constitution relation. And this is a work he did in collaboration with Martin's group, with Maria Elidaiana Pereira, et al., where they did what we plan to do in JPES, the calibration of the mass observable relation. So here we have the stacks of clusters using the mass proxy here, which is the sigma star related to the stellar mass. And we have the model fitted where the mass is one of the results, M200. And in here we have a relation between the M200 and the observable, the stellar mass here. And we fit a relation, and that's what goes in here. So this is what's done with CS82 data, which is 100 square degrees only. Then it's a very nice density of background source, 10 galaxies per arc minute. And with these things, we could constrain the mass scale in the 20% level. So this is this error over this quantity here. So we want to keep it down to the 5% level with JPEGs. But to do that, we need to know the shapes of galaxies, of background galaxies. And those shapes are severely impacted by the scene and the quality of the image and several parameters. So it's a very complicated measurement. And for that, there's a student of mine that just finished his master's and started his PhD called Leonardo Vieira, that worked in the mini JPEG data. Mini JPEG is an area of 1 square degree in the edges area, which we use it to have a preview of what JPEG will be. He used a very traditional method, the KSB, with some improvements. It's called re-Gaussianization method, to measure the shear of the galaxies, which has to do with the ellipticities. Okay, so we in general describe ellipticities in terms of E1 and E2, which are the two components. We could do like a model of ellipticity and a position angle as well, but the angle is awkward because of the rotation, so we prefer E1 and E2. So then we try to measure systematics on those measurements. So we have the measurement and then a multiplicative component from the true measurement. So G is related to the ellipticity of the galaxies. And they have, so this multiplicative parameter M here and two additive parameters. One that it is alpha E1 is a spill from the ellipticity of the PSF to the galaxies. So if we don't do the correction well, we have this leakage here, and it contributes as an additive term. So this is this alpha, this coefficient. So how much of the PSF ellipticity leaks into the galaxies? So this red line is without doing any correction, and the black line is after corrections, and as a function of the distance. And we're pretty happy with this result because it's well, the statistic is poor, but what we have is within the limits we can afford. And for the M part, the multiplicative correction, so it makes this line here between, so we are using CFHT data from the semi-area, which is much deeper, and therefore can be considered free from this kind of biases as our truth table, and we compare with our measurements here. If you have no multiplicative error, this cloud will be perfectly aligned with the one line. But what we have is this red line here. We have this M factor, but the error is of the order of the 1%. So we are quite happy so far. Plus, compared to other laser surveys that you might heard about, cluster lensing is much more forgiving because the signal is much higher, and we don't have to take so much attention to the additive components, because since we are averaging the tangential shears, if we have an additive component which is constant over the typical scale of arc minutes, where these measurements are made, it will cancel out. So our main concern is M, and we are happy so far with what we get. Of course, when we have the full camera, so this is one CCD camera, the full camera, what I show over there with the full Andromeda galaxy within, it's a huge camera, will present other challenges. So we do all of that by that time. So other thing we are trying, just to be innovative, is the use of convolutional neural networks. So here is Clasio and his groups collaborating with us. You heard about neural networks before. So we are using efficient nets from Clasio's the Bond group to train. We are using CFHT data that I showed that's much better than the. So CFHT is here in the bottom, and on the top is JPass. So CFHT have a much bigger signal to noise. So we can use those galaxies and those ellipticities and show that the neural network, those images, and say, well, those are the ellipticities, and learn from that, and then go measuring some other galaxies. So we did that, and we have a result which is almost as good as what we have with the KSB method. We only need to improve on the PSF deconvolution part, which the neural network is not doing, because we include or not include the PSF. It doesn't make any change in the result. So we still have to teach our network how to deal with different PSFs. But it's a method we are really invested in making work, because JPass will be the perfect test bed for this kind of studies. And of course, I didn't mention up to now that we have to find the galaxy clusters and to have an optical proxy from that. So how we are going to do that? So it's an optical survey. So we have to find data using photometry in a 2+1D space. Why it's 2+1? Because we have a very good handle on the projected in the sky part. We know exactly where galaxies are, but we have a lot of uncertainty on the third dimension, the redshift one, because it's not directly distance, and we don't have even the spectroscopic redshift. We have photometric redshifts. So that the main problem, and it's probably the thing that's affecting DES measurements, that's why they are so biased so far, one of the hypotheses, is the contamination caused by unbounded structures, but which are seen in the line of sight, that because of the uncertainty of photometric redshifts can be joined together and create artificial clusters. So there are methods that uses a lot of information about the nature of clusters and develop filters, apply those filters of the data, and detect clusters where these filters have maximum, as the Bayesian cluster finder or Amico, which is one of the methods in Euclid. And there are methods that uses the less possible amount of information. Assume that clusters are just over densities on this space, as the Voronoi tessellation from Paulo Lopes over there in the Valongo, and the PZ wave from Anthony Gonzalez, University of Florida, which among Amico are the two main methods for Euclid, which we're using here in São Paulo, PZ wave. So what PZ wave does is to use the projected positions of galaxies and photometric redshift PDFs to find clusters. So it slices the redshift space using the PDFs to calculate the amount of the galaxy which is within the boundary of those slices, and create density maps. And those density maps are filtered with a wavelet function, very simple, which is called a difference of Gaussians. So the difference of Gaussians is just that, the subtraction of a broader Gaussian by a smaller Gaussian, a narrower Gaussian. So all the structures which are larger than the broader Gaussian and smaller than the narrower Gaussian will be smoothed out. But the structures in between will be enhanced. And then we use typical size of clusters. So small sizes, 400, 500 kiloparsecs, larger sizes, 1.5, 1.4 megaparsecs. So we bracket the typical size of clusters. That's the only information about the physics of clusters we are getting there, and find clusters this way. So this is a map of the mini JPEGs made by PhD student here at Albrava, showing here some of the lowest redshift detections. And well, there's a whole richness method she developed, which is new as well, but a new way to estimate richness taking advantage of how well the PDFs of the photometric redshifts of JPEGs are. So here, of course, as usual, we have a lot of low richness objects and very few high richness ones. And this is a comparison from what we get from clusters found by very deep X-rays in the area. So the X-rays are those circles. And you see that we have actually found those clusters. And here's the mass, with 10 times to the 13 solar mass. Those are groups, not even clusters. So this is one cluster here, probably, which is more than 10 times to the 14. And we were able to find in low redshift structures with masses as low as 2 times 10 to the 13 here. We found most of them. We start losing some at higher redshifts, 0.6, 0.7, 0.8, but we still could find clusters or groups with mass of 6 times 10 to the 13, all the way up to redshifts of 0.7, 0.8. So that was very encouraging in our capacity of finding clusters. But for the purposes of cluster counts, we are more concerned with the low redshift ones because we cannot calibrate those high redshift ones with gravitational lensing. We are going to do that with stacked Sunyaev-Zadovich measurements. So we are going to have an overlap between the low and high redshift. But I'm going just to talk about the low redshift ones. So we estimated pureness and completeness for all the objects with higher than 5 times to the 13. And those are very important because the number here is the number of real clusters. So we have to take into account the contamination and incompleteness of any catalogs we are producing. And not only in the counts, but as well in the calibration of the mass observable relation, because the incompleteness won't affect it. But we have contamination, it will. But what we have so far is that we can have very good completeness and contamination, especially for the low redshift ones, from 0.4 to 0. But how about the overall systematics I mentioned? Because the point I was trying to make is that JPEGs will be able to do these measurements with a nice systematic statistical error, but with a systematic error which won't compromise the measure. So let's discuss that. So this is a table from the DES year 1 weak lensing mass calibration of the red mapper clusters. So we have results from the science verification, which is a 200 per degree area, and year 1, which is 1500 degree area. And DES have a density of background sources for lensing of 6.4. So for comparison, we have 2 for JPEGs. So we need a bigger area to have the same statistical errors as DES. So in the science verification, I put a green thing here because the systematic error was below the statistical error. And the statistical error was great, as big, because of the small area. Okay, so small number of clusters, etc. When we go to the year 1, so they decrease the systematics from 6 to 4%, but the statistical went all the way to 2%. And so they are already dominated by systematics. So they can go to year 3, year 5, large area, 500 square degrees, that this result won't improve because it's systematically dominated. So that's the work here is to decrease even more the uncertainties. So what are the main systematics that we know about? So shear measurement is one. So see the decrease from 4 to 2%. And we have already proved with mini JPEGs that we are in the same level of HSC and DES. I couldn't show here, but it's in the master thesis of Leonardo. So that was with the one CCD camera, which has yet to be proven with the big CCD, JPCam with 14 CCDs. It's a much larger area, which require, the optic is to be really, really good to keep the image quality over all this area. But remains to be seen. So far, we have reasons to believe that we can do that. And there are several other measurements which depends one way or another from photometric redshifts. So photometric redshifts themselves, which has to do with the lensing measurements, plus line of sight projections that I already mentioned on the cluster detection, and membership dilution. So the fact that we include cluster members when doing the weak lensing on the background sample, and this will dilute the sign. So all those things, they both depend on the photometric redshifts. And we think that we can do better than most surveys just because of the design of the 55 narrowband filters. And of course, there's nothing to do about cluster triaxiality, it's just nature. And modeling systematics, something that depends only on how well we can model things. So that's no really showstopper here. It's just how much more we can and are willing to put in our model. But let's see, the source of uncertainty depends on the photometric redshifts. So the photometric redshift parts, which are here, has to do with the uncertainty on the lensing critical density. So if we don't know the redshift of the sources, we get this number wrong, and we bias our measurement. So using the data from the mini JPEGs, we found for the galaxies we are going to use for lensing, the typical error we are going to have in photometric redshift is 0.013, which is quite low. So we did some simulations using these numbers, and we tried to see the effect on the critical density, and the effect on the critical density are all below the percent level. So 1% will be here. So it's a 0.5%, 0.2%, etc. So it is pretty under control, as we experienced. So it's probably be completely subdominant for JPEGs. So what about line of sight projections? So we are working with MOX now. We are going to have a very good handle of that. But what we have is the mini JPEG area, which is in here. And as an example, this is the paper from Matteo Maturi that we run Amico on this area. We have here, in this slice of redshift 0.24, a huge cluster in the area. But if we go to a slice of 0.36, we have another cluster. So the first cluster center is here. There is no sign of contamination of that huge clusters in here. We could disentangle very well. So Matteo and his group working on the kids survey, he was very impressed when he saw that, because in kids, that was not the same. And of course, here we have the opposite case. So we have two different redshift clusters, which have been detected by one. But in the overall, it seems that we are doing pretty well in this area. Soon we are going to have more quantitative results to show. So this is the precision for the photometric redshift of clusters. Since you have several galaxies, that's much better than the individual galaxy. So it's pretty low, which is as well very good for doing autocorrelation function of clusters, which is another way to measure S8. So membership dilution, we're going to do some tests, but we expect that the photometric redshifts will be good enough so we can differentiate easily cluster galaxies from the others. So 5 broadband deeper data, for instance, Rubin survey and others. Thank you, Martin. 5 minutes. I'm finishing. Won't beat, for more mind-blowing that it sounds, for the low redshift universe. Doesn't matter that LSST goes as deep as hell, because it has only the 5 filters, and therefore the photometric redshift is limited by this resolution. So you can have like 0 errors on magnitudes, but since you have only 5 or 6 points there, there's a limit where we can go in photometric redshifts. And JPass will be able to explore this niche in the low redshift universe to get this very, very good photometric redshift and apply that for several science cases. In this case, I'm talking about the cluster counts and how it helps. And another point I would like to make comes from this plot here, where I show that the inclusion of the loads of objects between 10 times to the 14 solar masses and 5 times to the 13 solar masses almost doesn't help when it comes to the calibration of the mass scale using weak lensing, because of how little signal these groups have. But the number is here. So in here you have the 1 times 10 to the 14, and in here 5 times 10 to the 13. It's a huge amount of objects. We cannot, and we are going to detect them with very low contamination and incompleteness, as our previous results shows. But we are not going to use them for measuring sigma 8. But we can do the opposite. We can have sigma 8, S8, and other cosmological parameters from cluster counts, from the clustering of galaxies, clustering of clusters, etc. We can predict how much of those groups we expected to find and compare with our results, our observations, and learn about that, because there are a lot of uncertainties on the formation of those objects. The role of baryons seems to be much more intense when we go in the group range rather than in the cluster range of masses. So there will be a lot of astrophysics of the formation of objects that we can potentially learn from this kind of data. So we have the unprecedented potential, because there's not a lot of surveys over there that goes that deep on the mass function in this area, in the mass. So we are going to have this group mass range to work, the redshift to work, which will be really nice. So that's the summary. Thank you very much. We'll try to take questions, but since I cannot hear you, maybe Martin can post here for me. Thank you very much.
Let's try once again. No sound. Okay. Do you hear from here? No, it doesn't work. Okay. So I guess we can try the phone, the phone option.
I can hear. Yes.
You can hear?
Yes.
Great. That simplifies life.
Sorry
Fantastic.
about all the mess, guys.
Okay, so questions for Eduardo. Either online or from here. Okay, so I have a question. You mostly put what you expect for JPass in the context of the other imaging surveys, right? And the advantage, of course, of JPass is the super precise photometric redshifts. although it's not that deep, but also the nice fact that you can do everything in the same survey, like mass calibration and so on. How does this connect with surveys in other wavebands like Suniev-Zeldovich? What do you expect in the same time scale from other probes, not like optical surveys?
Yeah, so the weak lensing calibration, which is key. Even for Suniev-Zeldovich and X-ray studies, the calibration of the mass observable relation is mostly due by weak lensing. So the optical part has to enter. And I mentioned only JPEG measured shears, which puts a strong limit. But in time, we are going to have a lot of public shear data from Euclid and other surveys that we can use and make things deeper, okay? So this is a kind of a pessimist view, the one I showed. One survey that people were expecting a lot, but it seems that won't deliver is eROSITA. The satellites have a finite lifetime, and it switched off because of the German-Russia thing. So it seems that it won't be as deep as expected. But of course we can. So I don't know for sure what would be the final numbers from them. So that can be, of course, a very interesting source of cosmology as well. I cannot tell exactly compared by numbers, and I'm not sure if we have. So we have ongoing Suniev-Zeldovich observations. We have already some the SPT and ACT. Those are very good. Those all detect mostly. Those will be very important for the mid to high redshift universe, because the Suniev-Zeldovich it decreases. It's more efficient on those redshifts, loses efficiency much slower than X-rays, for instance. And those will be pretty good, especially for using clusters for dark energy parameters. Because I didn't mention dark energy, because when we are only in the low redshift universe, dark energy doesn't change a lot on the number of objects. But if we can see the number of clusters in several redshift beams up to redshift of 1 or further, then we can see the effects of dark energy. And for that, Suniev-Zeldovich will be really important. But I'm not sure that they will beat the optical surveys in low redshift. Right. Because they detect only high mass objects, okay? The threshold in mass is much higher.
Thank you. More questions, either from the auditorium or online? Okay, if there are no other questions, I will ask another question. So you mentioned Euclid, that finally seems to be that it will be launched in July this year from an American rocket because of the Russian issue. How about, but okay, J plus is a half or something like that European. So there is an agreement with Euclid and so on. How about Roman, which is mostly American, but it will have the data will be made available right away. I don't know if the data products like shears. Is there any comment about the Roman side?
Well, of course, if we can access shear from those, there's no reason not to use. There's no comparison whatsoever between space-based shears than ground-based, especially from a 2.5 meter telescopes in continental Spain. Okay, so 2 galaxies per square arc-minute is not ideal, but the JPEG area is large enough that we can use that. But once we have or Roman or Euclid or any other source, we are going to use, and that will make our results much better.
Thank you. More questions? If not, let's thank again Eduardo.
Thank you guys, and apologies again for the mess.
No problem. Now we have Nathanael from the Valongo Observatory in person talk.
Pode deixar que eu estou mexendo aqui, por favor.
Okay, so So, hi everyone, my name is Nathanael Oliveira. I am an astrophysicist or astronomer. And now I'm doing my master's degree in astrophysics at Falun Observatory, working with Karim Menendez del Mestre. And well, we are working on the dark matter distribution in Milky Way analog galaxies. So let's go. This is a brief outline of the presentation. So I'm going to start with a brief introduction of dark matter and passing through our purposes. And then we can move on for our sample data and methods. So then I'm going to show you about our results on the dark matter distribution in Milky Way analog galaxies and a brief summary. So, okay, let's go. I usually start my presentations by introducing dark matter and stuff, but I think this is not needed for this audience. So let's get to just what's dark matter? And this is a big question. This is a billion question. And the answer is, we don't know. But one thing we can do is try to understand better how the dark matter is distributed in the universe, in galaxies, and stuff. So there are some evidences of dark matter. For example, using as a basis the standard model, we know that the universe is composed of energy and matter, where around 85% of the matter is in the form of dark matter. So we hope that dark matter, sorry, I'm trying. So we expect that dark matter has dominated the primordial composition and governed the formation of galaxies and grouping of clusters and large-scale structures as a whole. So the primordial filaments of dark matter coalesce and form what we can, let's say, gravity nuclei. So where that subtracts the dark matter, the baryonic matter. So, but one of the most concrete evidences of dark matter are the rotation curves of galaxies, especially the spiral ones. So a rotation curves are plots that shows how the velocity of objects like, for example, stars or gas evolves as these objects move away from the galactic center. So as you can see here, okay. So we know that galaxies have the mass concentration, or at least the baryonic mass concentration, in the central regions. But so based on this, what we hope to see is something like this profile. But what we really see is something like that. So the rotation is quite different. And this was seen firstly by Vera Rubin in the 70s. So how is it possible? And there are some studies that try to explain, to understand this behavior using modified gravity, for example. But here we are trying to understand using dark matter. So the dark matter is responsible for that behavior. So this brings us to our hypothesis. So let's say that dark matter does exist, but how is dark matter distributed? So through the rotation curves, we know the dynamical mass profile of a galaxy, but decomposing these rotation curves, we can see how much mass is due to the bulge, for example, or gas, or disk, or dark halo. After all, that's what we are trying to find out, the dark halo. So we are looking for plots like this, but on a smaller scale. We want to know the dark matter distribution in the internal structures of galaxies. But why is this important? And well, the current decompositions in the literature are very biased by the large number of free parameters. So our method tried to reduce the free parameters using, for example, observational data of nearby Milky Way-like galaxies. I'm going to the details later. So the second main objective of this work is to collaborate to experiments that try to understand dark matter, that try to detect dark matter, exactly. So there's a lot of candidates of dark matter, for example, metros, axions, and wing interacting massive particles, or WIMPs. And that last one is one of the most promising dark matter candidates. So there are some features on WIMPs, but I want to highlight two in particular. The first one is that WIMPs are a type of dark matter, of cold dark matter, what means that there's no relativistic velocities involved. And the second one is that the interaction between WIMPs and baryonic matter is only via weak force, which is a problem because weak force has very low outcomes. Well, I'm not going to the details on dark matter direct experiments, but for example, the Lux Zeppelin, which is located in South Dakota in the USA. But basically, the idea behind this experiment is that a WIMP pass through the xenon tank, 10 tons of liquid xenon tank, and then the WIMP will collide with a nucleus of xenon, and then the nucleus will produce some electrons. So we'll liberate some electrons that by the time will, let's say, float to the top through an electric field. So in the top, this WIMP will produce a combination of characteristic light beams that will be detected with around 500 photomultiplier tubes. So what's the problem? Where our work come in? And basically to understand, to derive the number of particles these experiments hope to detect, these experiments need local dark matter density estimates. And the current estimates are strongly biased due to both the profile of the dark matter halo of the Milky Way and to local conditions of stellar kinematics that present large uncertainties. So we want to do that, to estimate the local dark matter density using mirror galaxies. And this connects us to our sample data and methods. So the first thing when we are trying to define a sample is to define a sample based on galaxies that have data from the literature. So we are interested in two type of data in particular, H1 distribution and stellar distribution. So So the H1 distribution is important to us, especially because, as you can see here, I put two images of the same galaxy centralized at the same coordinate, and both images are scaled. So here we can see that the stellar distribution is quite lower or less large than the distribution of atomic hydrogen gas. So that's why we are using hydrogen gas. With the dark, with the atomic hydrogen distribution, we can see not only how baryonic matter is distributed, but also we can see and we can study how dark matter is distributed in the internal structure of galaxies. So how do we do that? Well, our sample is defined based on three main surveys. The first one is Viva survey. We have access to the data cubes through the Viva survey via a imaging of Virgo in atomic gas. So these are some technical information of the survey. For example, the spatial resolution around 400 parsecs. And well, as we have seen, this is important because the H1 distribution is in general around 3 times larger than the stellar distribution. So H1 is a good dark matter tracer. And also for the H1 distribution, we use Thing survey, the H1 nearby galaxy survey. So again, some technical information. The spatial resolution, for example, is quite better than the Vivas. And finally, we can use the data from the S4G, which is the Spitzer survey of stellar structures in galaxies. So the spatial resolution, again, is quite better than the last ones. So, but why are we using mid-infrared as a stellar tracer? And basically, there is something called initial mass function that says to us that only around 5% of the stars formed in a molecular cloud are more massive than the sun. So mid-infrared is a good stellar mass because the population of a galaxy is dominated by low mass stars. So this is our sample. Our sample is defined based on 3 main criteria. The first one, morphology. So we want galaxies that have a morphology like similar to the Milky Way. So we only want to get spiral galaxies. Second one is a stellar mass and the maximum rotation velocity of the atomic hydrogen gas. It seems a bit random, use the maximum velocity of the atomic hydrogen gas, but this is maybe the most important criterion. It's because when we cut with the maximum velocity of the atomic hydrogen gas, we select objects that have not only a baryonic matter distribution similar to the Milky Way, but also a dark matter distribution similar to the Milky Way. So here we have the objects of our sample, and here I plot a comparison between our sample and the parent sample of S4G. So this is the face of our objects, our galaxies, and the H1 spectrum. So let's go to the methods. Well, deriving rotation curves. Through the Viva survey, we have data cubes that we can analyze to derive the flux and velocity maps. It's important to do a correction through redshift. That's because the universe is dynamic now. Well, and the method we use is to derive, is to is to trace a line over the velocity map. So as you can see here, this is the line, and our code tilts this line over all possible directions to find out where is the inclination of the major velocity gradient. So when we do that, we can ask to our code to extract the velocity information present in each pixel that is under this line. So we can plot as a function of the distance from the center of the host galaxy, and there we have a rotation curve. So let's go to the dark matter distribution in Milky Way analogs. So a rotation curve is a superposition of different contributions in a galaxy. For example, bulge, disk, gas, and halo. So we have to study each contribution separately. That's because each distribution has a different symmetry, for example. So for the bulge, we are using the Harcris profile. That's like something like this as a function of the bulge mass and the effective radius of the bulge. Disk, we are using cosmic profile, gas, an exponential disk of gas. And halo, we are using Naval-Frank-White profile. So the difference between our work and other works in the literature is exactly that we are trying to reduce our free parameters. So as you can see here, we have a parameters, for example, mass of the bulge or mass of the disk, and we are trying to decompose the stellar mass to effectively calculate these parameters. So we have less parameters or less free parameters than the others works, for example. So to do that, we use this relation that's from Skew and collaborators in 2012, and they derive the stellar mass of each component, like the bulge or like the disk, from the flux in 3.6 and 4.5 microns. And we have this data from the S4G survey, so we can do it by ourselves. The same thing for the gas. So we use this relation from Catinella and collaborators in 2000, the first paper of 2010. And there we have one of our decompositions. So this decomposition shows the different contributions for the bulge, for the disk, for the dark halo, and for the gas. So here we have our data, the black circles with error bus, and the region of reliability, I don't know, 1 sigma confidence, yes. So this decomposition especially returns to us a chi-square per degrees of freedom around 1, which is very good. And we can see in this particular galaxy, which is NGC 2903, we have around 90% of the total mass due to the dark components. A mass distribution, so we can decompose the stellar distribution, the gas distribution, and through the rotation curve, we know the dynamical mass. So we can put everything together, and then we have a mass distribution as a whole. So, okay, it's important to pay attention. This plot is something like this, but color-coded by the dark matter contribution. So it's important to pay attention to this region. Where is dark matter? There's no dark matter there. But is it possible? And the answer is, one of the reasons that we don't see any dark matter there maybe is because of our tracer. H1 maybe does not represent the internal dynamics, this region. Good. So possibility is to use carbon monoxide or H2 alpha line to describe this region. So that's what we are trying, we are going to do in the near future. So other results, local dark matter density. So it's a big objective to us. And here I put some estimates from the literature. For example, Fabio Iocco. That's very important, especially because their estimates are quite similar to our estimates. And here I put our estimates, our range of values for the local dark matter density. So we suggest a dark matter density around, in the solar neighborhood, of course, around 18.39 giga-electron volts per cubic centimeter. So, well. And the last plot I want to show you now is the stellar to halo mass relation. This plot has been extensively investigated in the literature because it is important to determine how the star formation molds the halo mass O vice versa. So here we have our data. Our galaxies are color-coded according to the atomic hydrogen mass. And here I put also the results from the policy and collaborators in 2019. Manserapinha, that's a very recent work, September of last year, and the Moser in 2013. So we can see that there is a relation, and well, our results are quite similar to especially the Post et al., but the inclination of this kind of relation, linear relation is less steep than the Post have found in 2019. So our results are in agreement with the previous ones, but especially with the Post et al. So a brief summary of the work. In this work, we use an independent approach to model the dark matter distribution in Milky Way analog galaxies. So we derived and decomposed the rotation curves of the sample. Then we found that the contributions of baryonic and dark matter are almost similar around the solar neighborhood, and this has very deep let's say, something that we have to investigate because it is an important result. So we suggest a new local dark matter window. And what's next about the future? So now we are submitting some proposals in radio to observe atomic hydrogen by ourselves, and we got some time in radio with the GMRT radio telescope in India. And well, I'm very excited about that because we are trying we are going to observe and collect our own data, and the first paper will come out soon. So thanks a lot for the attention, and well, that's it.
Thank you. We have time for questions. Questions from the audience here. Remote questions. Okay, I have a question regarding the last slide that you put. So what do you expect to gain using this telescope in India? What it will add in terms of resolution, depth, or new objects?
So it's going to be in Portuguese. Well, a gente já tem dados de rádio, tanto com o VLA como outros levantamentos também, mas o ponto é que agora a gente vai poder fazer os nossos próprios dados e, sinceramente, a quantidade de galáxias análogas à Via Láctea, tanto com o levantamento S4G, que é um pouco maior do que os outros que eu mostrei, é significantemente pequena comparado ao que a gente pode fazer. Então, uma opção e uma ideia, é justamente a ideia por trás de coletar nossos próprios dados, é que a gente vai poder desenvolver uma amostra que não tem dados observacionais em H1 ainda, mas que a gente pode, a gente pode encontrar por nós mesmos. Então, assim, dá para enlarguecer o sample, a amostra e, observar por nós mesmos. Então, a gente vai ter os nossos próprios dados e, consequentemente, ter resultados um pouco mais robustos ainda, porque a gente vai conseguir ter uma amostra maior e, consequentemente, uma análise estatística melhor.
Obrigado. Thank you. More questions? Sim.
So I know your work, Nathanael, but it occurred to me a question in I think it's slide 34, perhaps, when you showed the plot with the stellar mass as a function of virial mass. Because I remember this plot when it was very different, and I was I'm very happy to see that they occupy this this region. Can you remind us where the Milky Way is? Because these galaxies are not Milky Way analogs. I mean, only yours are. But the Milky Way is somewhere around there. I wanted to know how you expect if a more careful choice of those parameters that are not free parameters in your case, because you have the stellar mass, the stellar light decomposition, do you expect them to change in, I mean, going closer to that location of the Milky Way analogs? Because I know this is something that you were mentioning that you would like to do a more careful decomposition than what has been published. And I was wondering if this would perhaps bring it down, and would that be good with respect to the location of the Milky Way in this plot?
Ok. So, com a massa que a gente sabe que a Via Láctea tem e com, enfim, algumas características, é tudo um pouco complicado também de entender para a Via Láctea, porque afinal de contas a gente está dentro dela, mas é esperado que ela esteja mais ou menos por aqui. Então a gente não espera que os nossos resultados estejam muito distantes disso. Então, bom, a gente espera que ela esteja aqui e com essa amostra maior, a gente vai poder fazer uma análise estatística melhor, então a gente vai poder concentrar exatamente onde a gente quer, uma vez que a gente vai ter mais dados e a gente vai ter mais recomposições. Então... Sim.
Thank you.
More questions to Nathanael?
Do you think this work can be extended to high redshift, for example?
Ok, sinceramente não. Eu acho que não, porque os dados que nós usamos, eles têm uma resolução boa, mas, sinceramente, às vezes eu até acho que poderia melhorar, que a gente tem algumas dificuldades por conta da resolução e são galáxias que estão no universo muito local. Redshift em torno de 0.001. Então, eu diria que se você estender para, sei lá, você trabalha com galáxias em alto redshift, então você sabe. Mas se você estender para, sei lá, 0.9, vai ser muito complicado de fazer as coisas que a gente faz com galáxias que estão do lado da Via Láctea. Então, acredito que talvez possa ter um bom resultado. Inclusive, eu tenho uma recomendação para você, o trabalho da Nikki Pozzi, que está na Universidade de Groningen. Ela basicamente faz exatamente a mesma coisa, só que com galáxias em alto redshift. Só que o fit é claramente diferente. Então, assim, eu diria que é um desafio, mas eu acho que pode ser feito, só vai ser muito mais complicado e talvez não tenha um resultado tão robusto quanto de galáxias no universo local.
But do we found this type of galaxies in high redshift?
Sorry?
Milky Way analogs.
Okay, yes.
Yes.
Inclusive o trabalho da Nick tem galáxias análogas também.
Mais perguntas? More questions? Yes. Thiago has a question or a comment.
É só um comentário, na verdade, sobre essa questão de alto redshift, porque eu acho que a dificuldade, Amanda, é a questão de conseguir os dados de rádio em alto redshift, principalmente com essa resolução. Então, a gente está entrando numa era nova, imagino que o SQA vai conseguir fazer alguma coisa, então, pelo menos, você consegue, imagino que a gente vai conseguir ver as galáxias, talvez não resolvidas. Você consegue ver a velocidade de rotação a partir daquele perfil integrado, né, com aquele double horn. Isso talvez dê para fazer. Resolvido, teria que ver. Não tenho minhas dúvidas. Dependendo da resolução que a gente conseguir, pode ser complicado. Definitivamente nada parecido com a resolução que o Nathan consegue para galáxias próximas desse jeito, assim, em termos de escala física na galáxia.
E só um comentário sobre isso. Bom, como eu falei, tem uma diferença gritante entre a quantidade de dados que a Nick, por exemplo, que é o trabalho que eu estou mais habituado, faz, especialmente porque, como o Thiago falou, é difícil resolver. Então, assim, por mais que tenham galáxias em torno de 0,9 de redshift, a quantidade de pontos observacionais que ela tem no trabalho dela é 2, 3. Então, assim, é complicado você fitar alguma coisa e querer ainda decompor esse fit em diferentes contribuições. Então, assim, eu acho complicado.
Okay, so let's thank again Nathanael. So before we go to lunch, well, first apologies because today we got a bit delayed, but we start at 1:30 anyway. So those that are interested in going to Belmonte for the happy hour after the meeting, please put your name in the list outside because we'll make a reservation. The idea is to go directly from here. And of course, if someone wants to donate, we are collecting money for the coffee breaks. You can go Pix or cash close to the coffee break. Sorry for some people enter and some people, so we have renewed people. Sorry for those that heard me saying this infinite times. Okay, let's go for lunch. Hoje vamos lá.
Oi, boa tarde. Tem alguém aí?
Clarissa, are you there?
Yes, I'm here. Can you hear me?
Yeah, perfectly.
Perfect.
Hi.
May I share my screen?
Yeah, sure.
Can you see?
Perfectly, yeah. Thank you.
Let me just stand here. All right.
So, welcome back everyone. So now we're going to continue our program with the talk by Clarissa Siqueira. So Clarissa, I'll let you know when you have 5 minutes, okay?
Okay, thank you. So it's a pleasure to be here. I would like to thank the organizer of the event. I am currently a postdoc at the Instituto de Física de São Carlos from the Universidade de São Paulo. And my supervisor is Vitor de Souza. And I will talk today about probing secluded dark matter in the next generation of high energy, very high energy gamma ray observatory. So I will start with a brief motivation, then I will follow to the main experiments that we use in this study, the CTA and the SWGO. And then I will focus on the particle physics point of view for the dark matter problem, talking a little bit about the evidences and the dark matter relative density, the detection methods, with a focus on the indirect detection method. And then I will follow to the secluded scenarios and go to my conclusions. So we know that we have several evidences for the dark matter existence, and they come from the different scales. They come from galaxies and galaxy clusters, and from the CMB being the cosmological case. So we have these evidences for the dark matter existence, and they lead to an abundance of dark matter in the universe that need to be approximately 27% of the energy budget of the universe. And basically, probe dark matter via indirect ways, a very interesting one, because we can access energy regions that are inaccessible in underground detectors, for example, like the xenon 1 ton and the LHC. And we also may probe some models that cannot be probed with these experiments. So I bring this picture of the Milky Way, where we have here several wavelengths of the Milky Way, looking at the Milky Way. So I found this picture very interesting because we see how choose different wave bands can give to us different information about the several astrophysical objects. And here, in this case, we will focus on the gamma ray searches. Of course, we have several instruments to make it. We have ground-based and space-based telescope, each one looking at different energy bands. And for example, here we have a satellite like the Fermi-Lati looking at gamma rays, for example, but we also can probe, we can look at these signals from underground detectors, as we will see. So basically, how can we detect gamma rays? As I already said, we have these space-based telescopes like the Fermi-Lati, for example. They directly detect the gamma ray that's entering in the Earth, our atmosphere. So we also may have these ground-based telescopes like particle detectors with Warren Cherenkov, like the SWGO will be and the HAWC currently is. So these kind of instruments may detect directly the shower produced by the interaction of the gamma rays with the atmosphere. So we also may have these ground-based telescopes like HES, for example, where we may detect the Cherenkov light emitted by this shower, and we also may detect this kind of gamma ray particles. So basically, all of these instruments, they are complementary. They can probe different energy intervals, like we can see here. They have also different field of view. For example, a particle detector have a larger field of view compared to the ground detectors, like the CTA, for example. And also, we have the uptime, as some of them may look at the sky continuously, like the Fermi-LAT, for example, and the SWGO in the future. But the CTA, for example, we need a clean light sky in order to make our detection. So they are complementary in several ways. We need all of them, actually. So basically, the CTA will be is under construction now. We will have more than 100 telescopes located in both hemispheres. Part of them located in Paraná, Chile, and the other part in La Palma in Spain. They will cover an energy of 20 GeV to 300 GeV, and it uses the Cherenkov light in order to make the detection of these gamma ray particles entering in our atmosphere. So basically, the whole of Brazil in CTA, we are actually building. We designed it and built this structure of the medium-sized telescopes. Actually, we have other contributions in the theoretical part. For example, we are studying Lorentz invariance violation. We are studying dark matter in the theoretical point of view, and we are also studying, for example, the propagation of the gamma rays from extragalactic sources. We are also study how this we may reconstruct this shower produced by the interaction of the gamma ray with the atmosphere here. And we have also people working in the distinction, for example, of a signal from a gamma ray or from an positron or a hadrons and so on. So we have several people working on this project from different universities, actually from CBPF, from the USP and Unifesp, and several other contributions. So the SWGO is also a particle detector that will be built here in the southern hemisphere. They will cover a large energy fraction from hundreds of GeV to hundreds of GeV. They also detect the Cherenkov light produced by this shower, and they have this. They are able to look at this region of the sky that are not accessible by the experiment HALC, for example. So one of the main aims of the SWGO is also study the dark matter problem. And here we have an interesting picture of the sensitivity flux, the flux sensitivity for each of the experiments we talked about. For example, here we have HALC, and here we have the sensitivity of the CTA, and here we have the sensitivity of the expected sensitivity for the SWGO experiment. And basically, they are probing all of this region here above these lines here. So the future experiments, for example, the CTA compared to HALC, will increase the sensitivity in almost 1 order of magnitude compared to all experiments that we have now, as soon as the SWGO will be also competitive and enlarge the sensitivity compared to the current experiments. Basically, the aims of these very high energy telescopes are several, including understanding better the cosmic ray acceleration transport, cosmic ray observations, and monitoring the transient sky, and also test to probe physics beyond the standard model, like Lorentz invariant violation, primordial black holes, and dark matter. And dark matter will be the main focus of this seminar here. Basically, why we believe the dark matter is made of particles. We know that, for example, dark matter can be made from primordial black holes. We have a seminar from this point here, but here we will focus on this particle dark matter. Basically, the evidences, all of the evidences that we have points towards are some interesting characteristics that the dark matter particle needs to be. For example, we know that the dark matter needs to be neutral and also need to be weakly interacting, non-baryonic, cold or warm, give the correct abundance that we observed by the CMB, and also be stable because it's present in the beginning of the universe and it's also present now. So the main candidates nowadays that fulfill all of these characteristics that the dark matter need to be is the called WIMPs, which are the weakly interacting massive particles. So they have a typical mass in this electroweak scale from the GeV to TeV range. It's important to say that the standard model of particle physics does not have a candidate to explain the dark matter problem. So the dark matter is directly related to physics beyond the standard model, like, for example, the neutrino mass that cannot be explained by the standard model of particle physics. So, but how can we produce these dark matter particles in the universe? If we expect that this dark matter is present in the early universe equal to the standard model particles, they can be in thermal equilibrium, so the dark matter particles produce standard model particles and vice versa. So as the universe expands and cools, this graphic is very interesting because it's the beginning of the universe. Here we have the quantity of dark matter in the universe, and in the beginning it's constant. So when the universe cools, since the dark matter is heavier than the standard model particle, at some time the standard model particle will not have energy enough to produce these dark matter particles, and we have this exponentially decay here until the point where the dark matter annihilation rate are comparable to the Hubble rate, to the expansion of the universe. So basically the universe expands faster than the dark matter particle may interact. So at this point occurs what we call freeze out. The abundance of dark matter remains constant in the universe. So this value for the abundance of dark matter is given by the Planck satellite with a high precision, which needs to be 0.12. So in order to get the most important point here is that in order to get the right relative density of the dark matter in the universe, we need to have a cross-section which is in the electroweak scale. What's the most interesting point here is because this cross-section can be accessible can be detectable for our current experiments. For example, we have several of them, including the xenon experiments and the LHC. Every experiment like this are looking for the signals from dark matter that I will talk a little bit more about now. So we have this kind of detection methods. We have this direct way to probe this dark matter particle. Since we are embedded in a large halo of dark matter, we may expect that the dark matter particle may scatter with our the particles of our underground detectors, like the xenon 1 ton, for example. And we also may have the production of dark matter via colliders, like the LHC. We also can have the collision of a proton-proton collision producing dark matter in the final state. So, and we may also have this indirect method where we may expect some stable products of the dark matter annihilation here in the Earth. So I will focus on this indirect detection method. As I already said, if we have regions, these regions in the sky, we may have this annihilation of dark matter particles producing these standard model particles. And these standard model particles will quickly hadronize and propagate until us, producing directly pions, for example, and these pions will produce gamma rays. And it also can produce neutrinos and antimatter, for example. Why we focus on gamma ray searches is basically because gamma rays they point toward the source. They are not deviated by magnetic fields in the galaxy. Also neutrinos. However, neutrinos are more difficult to detect than gamma rays. So this is why usually gamma rays are called the smoking gun for indirect dark matter searches. So when we are doing this kind of analysis, we need to take into account some things, some key ingredients for basically to make our analysis. So we need to know, for example, we need to choose some targets. I told you that we need to have some dense regions in the sky in order to have an annihilation of dark matter into standard model particles, for example. And we have some targets like the galaxy center, the dwarf spheroidal galaxies, and the galaxy clusters, for example. We need to choose a channel, for example, via BB bar, via tau, mu. We also need to know what's the dark matter distribution in our galaxy. We saw several times here in this event that we have several possibilities for them that I will talk a little bit more in the following. And we need to choose this final state particle, which can be gamma rays, neutrinos, and charged particles. And the focus of this talk is on the gamma rays. We also need to take into account the background related, and for example, what's the energy related to interesting for our case, in order to see what kind of experiments is more interesting for our analysis. So for the dark matter distribution, we have these possible profiles. Actually, it's not easy to make this kind of simulation. So we have simulations just with dark matter, and we including baryons, for example, and they lead to different kind of profiles, like cusped profiles, this kind of profile like NFW and NASTO. And we also have the choroid profiles like Burkitt and isothermal, for example. Of course, when we are doing an analysis using, for example, using the galaxy center or dwarf spheroidal galaxies, we need to choose which kind of J factor, which kind of distribution, this distribution of dark matter we may use. For example, here we see that we have a large discrepancy here in the inner part of the galaxy, and they converge to the same point in the outer part of the galaxies. This is just because in this region we have this dynamics of the stars, and we can use that in order to get the right distribution of dark matter. However, when we are looking at the central region of the galaxy, we have this huge discrepancy, and we need to choose, because we don't know when we are looking at the galaxy center, for example, we don't know what's the distribution of dark matter in the center of the galaxy. So we need to fix one of these profiles. This is what all of the current experiments do. We need to choose some of these profiles in order to make our analysis. So this will lead to discrepancies between different chosen profiles. So about the targets, and what we call the local targets are usually the dwarf spheroidal galaxies and the galaxy center. Dwarf spheroidal galaxies are very interesting to look for dark matter signal because they are predominantly composed by dark matter. And they are also very clean targets because they are free, almost free from background. And actually, the most stringent limits from direct detection come from combinations of dwarf spheroidal galaxies, and they are excluding the cross-section that provides the right relic density for the dark matter masses below 100 GeV. And these strongest limits come from the Fermi-Latti experiment. And we also may look at the galaxy center, the central region of our galaxy. When we are looking at this region, usually we exclude the latitude, the B less than 0.3, in order to avoid the central region of the galaxy, which is very, very bright, and we have a lot of background here. So this region is very interesting because we know that there is a high DM density in this region, and compared to the dwarf spheroidal galaxies, it's much more higher than that. So they actually we have also limits from the Hess experiment. They are not so strong, but we will see that the CTA in the SWGO will give a very strong and complementary limit to the recent results of the Fermi-Latti satellite. So talking about the extragalactic targets, we also may look for signals from dark matter annihilation in extragalactic targets like Andromeda, Virgo, and Coma cluster. However, we have a lot of uncertainty related to it because of the propagation and so on. And usually they provide less stringent limits. They are provide less sensible limits to dark matter models, for example. So by the end of the day, when we talk about the targets, we have, for example, here, this is an interesting picture also. We have the maximum expected flux here coming from, for example, the galaxy center. The galaxy clusters also have a huge quantity of dark matter, however, have large uncertainties, and dwarf spheroidal galaxies do not have a high DM density. However, they are free from background, so they produce robust predictions. And these are the main targets that we use for the indirect dark matter analysis nowadays. So about the final states, as I already mentioned it, we may have charged particles in the final state. So the problem with these charged particles is that they have a diffusive propagation because of the magnetic field, and they are usually easily deviated from the source, while the neutral particles like neutrinos and gamma rays, they have an unperturbed path. So they propagate directly to us, and we have this information about the location of the source, and this is an interesting feature. So, for example, about the associated background, we need to take into account, especially when we are looking at the region of the galaxy center, because we have a lot of background. Usually, they come from the cosmic ray sources, and the cosmic rays propagate and interact with the medium, with the interstellar medium, and produce also gamma rays and it usually they call this the galactic diffusion gamma ray emission, and we need to take this into account when we are doing an analysis. Of course, we have another kind of backgrounds. This is just an example. Here we have a picture where we have the expected signal from dark matter. For example, here in this purple line, we have dark matter producing the WW in the final state for a 2 TeV dark matter particle. And here above, we have several backgrounds that are that come from the galaxy center, for example. And what we need is to find the dark matter signal below of all of this background. So you already saw this formula here. We have this gamma ray flux, and this gamma ray flux depends part on the particle physics, and the other part on the astrophysical part, which depends on the density of dark matter in the medium squared. And some important points here are, for example, the spectra of the dark matter that can be different depending on the channel produced here, on the particle produced here in the from the annihilation of the dark matter particle. For example, here the spectra produced by tau leptons in the final state. So basically, these particles propagate and are producing gamma rays in the final state when these particles propagate into us. And also we have here B quarks. They usually quickly hadronize, producing pions, and these pions will also produce these gamma ray particles that can be observed here in our telescopes. So what we have at the end of the day, we have, for example, the DNDA, where we use to compute the flux of dark matter, and this flux of dark matter is here, for example, and here we have a lot of background here, and we need to see this bump here over the background. So also when we, as I already said, when we are looking at the astrophysical part with the J factor, we need to choose some of these profiles for the dark matter distribution in the galaxy, and some of them are more cuspy that will provide usually stringent limits, and they are also, we have also the chord profiles that provide less stringent limits. So the main, most important gamma rays experiments nowadays are the Fermi-Latti and the HAZ experiment, and they cover different energy range. For example, the Fermi-Latti are providing the most stringent limits coming from dwarf-spheroidal galaxies, while the HAZ experiments is looking at the galaxy center, and it's also given strong limits in the high dark matter, for higher dark matter masses. So the future CTA and SWGO will provide a huge enhancement in sensitivity compared to HAZ, as we will see in this plot. Here, for example, we have the plot annihilation cross-section versus dark matter mass for different experiments. Here we have the SWGO in this gray line. Here we have the CTA with this red line. And here we have the HAZ experiment and the Fermi-Latti experiment, this blue line and this green line here. So the sensitivity of the future experiments will be enhanced in almost one order of magnitude. So everything above these lines here, this blue line, this green line here, are excluded by the current experiments, but the CTA and the SWGO will be able to probe a region that was never probed by these experiments, and maybe they will lead to see some signal of dark matter in the near future. But until now, I just talked about limits and sensitivities, but we observed some signal from dark matter annihilation. For example, we have some of them. There has experiments observed nexus in the TeV scale that may be explained by dark matter annihilation. Also, the AMS2 experiment observed a positron axis that can be explained also by dark matter. And the Fermi-Lat also observed an axis in the galaxy center region in the GeV range that can be also explained by dark matter. However, we don't have sure about the about what is giving this signal. Maybe pulsars can also provide this spectrum. So we cannot say for sure that the dark matter is providing this access, but they are access that are observed especially in the galaxy center, that can be explained by a dark matter annihilation. So at the end of the day, what we have basically is that WIMPs, as I told you before, are the most interesting candidates to explain the dark matter problem in the particle physics point of view. However, when we are looking at, when we are studying different models, different extensions of the standard model that provides WIMPs, this is basically the picture that we see. This is basically a picture of the coupling versus the dark matter mass. And this red line is the right relic density, the region that provides the right relic density of dark matter. And these shaded regions here are excluded by the current experiments. So at the end of the day, what we see, what the region that can escape the current limits are just the peak of the resonance. This happens also, for example, when we have a Z prime mediating the interaction between the dark matter and the standard model particles. So what we do in this sense, we have to look for another possibilities. We have to look for another scenarios that can explain the dark matter problem. For example, we may look at lower mass particles like sub-GeV particle dark matter, or heavier dark matter particles like several TeV dark matter particles, or look at some possible change on the cosmology, like including non-standard cosmology, or even axion-like particles. And I will focus today on the kinds of on this type of model, which are usually called secluded models. They usually provide interesting direct signatures. They can explain, for example, the excess observed by the Fermi-Lat without conflict with other observations from dwarf spheroidal galaxies, for example. And they also can be tested in planets or stars, for example, if we expect that the dark matter may annihilate in mediators that do not belong to the standard model, and then these mediators decay into standard model particles. So they are also well-motivated models. They appear in different extensions of the standard model. And so they are actually very interesting candidates to explain the dark matter problem. So basically what we have in secluded models, we have this visible sector, which is composed by the standard model particles, and we have a dark sector, and we have a mediator that connects the visible sector to the dark sector. And if we choose the mediator to belong to the dark sector, we may have this interaction where the dark matter do not couple directly to the standard model particles. Instead, the dark matter annihilates into these mediators, and these mediators will subsequently decay into standard model particles. The most interesting aspects of this kind of scenario is that they can escape from the stringent limits from direct and collider searches, and they also can be probed by indirect detection experiments. And in this analysis, we make a model-independent analysis, choosing this mediator as a vector or a scalar, and we compute some limits for indirect detection experiments. So here, but
what is sorry to interrupt you? You have 5 minutes, okay?
Okay, perfect. So here we have the gamma ray spectrum for the secluded scenario. We have basically the spectrum generated for a secluded model. We usually compute the NDE for the center of mass of the mediator, and we make a boost to the dark matter mass. And this what we need to have in mind in this, basically this computation, is this epsilon F factor, which relates the mass of the chain, the mass of the final state particles over the mass of the mediator. For example, here we may choose different channels like BB bar, tau-taus, and electrons and muons, and so on. So this is our results for this gamma ray spectrum. For the leptonic channels here, we have this spectrum here. We also put here in the plot the direct tau-tau annihilation and compared to the secluded model. Usually they lead to a broader spectrum because instead of producing two dark matter particles, you are producing two standard model particles, you are producing 4 standard model particles. And here we have the spectrum for the hadronic channels. For example, for BB bar, for quark, and for quarks, the blue and the purple lines here, remembering that we are changing the relation between the mass of the mediator and the mass of the final state particle. Is given by this epsilon F equal to 0.1 and 0.01. We do not have a huge discrepancy between these two different choices. So basically here we have the key ingredients for this work. We look at the galaxy center for TeV gamma rays, looking at the galaxy center. We choose the central region of the galaxy, and we make our analysis for the HAZ, CTA, and SWGO, of course, excluding this bright region of the sky in order to avoid the strong background that we have in this region. And we choose several channels. The mediator going to electrons, muons, taus, quarks, and beads. So for the DME distribution, we choose the Enasto profile, and we also saying that we compute the limits for the HAZ experiment and the SWGO and the CTA using 254 hours for the HAZ and 10 years for the SWGO and 500 hours for the CTA. So here we have our results. This is very interesting because here we also overlap the limits from the Fermi-Latti experiments, and this is basically what we expect, right? We have the limits for here, for example, for the Fermi-Latti experiment, and the limits for the HAZ experiment. In the future CTA, we probe all of this region here that enhance the sensitivity in almost 1 order of magnitude we see also some interesting characteristics. Usually, taus provide most stringent limits because they quickly hadronize and produce pions, neutral pions that will give these gamma rays. So, for example, if we have taus in the final state, we will be able to probe the region that provides the right relic density of dark matter for a large range of dark matter mass for almost 100 TeV mass of the dark matter particle. So this gives to us a hope that this future experiment may see a signal from dark matter annihilation, maybe from secluded models or not for a direct annihilation also. So here are the results for quarks. Usually they provide strong limits like the taus because of the hadronization and the production of the neutral pions. So here we see how they will be complementary to the Fermi-Lach experiments for the higher mass regime, and also how we will be able to enhance the sensitivity compared to the HAS experiment. So I finished my talk here. We know that we have a big mystery to solve. The dark matter problem is one of the big mysteries we have in physics nowadays. So WIMPs, what we saw is that WIMPs are excellent candidates. However, when we try to embed the WIMPs in some extensions of the standard model, it's really hard to escape from the current limits that are very, very strong. And the community are looking for other possibilities, maybe alternative production methods or secluded models or non-standard cosmology and so on. The future, very high energy gamma ray observatories like the CTA and the SWGO will be able to probe a significant fraction of this parameter space for secluded models. And maybe in the near future, we may see a signal from dark matter coming from these experiments. So thank you very much for your attention.
Thank you so much, Clarissa. We have time for one question. So any questions from the audience and also from the Zoom? If you have any questions in the Zoom, please unmute yourself because we can see the chat. So we have a question.
Hello, I'm Igor, and I have two questions for you, but they are very linked to each other. First of all, thanks for your presentation. The question is, what would be those mediators you were talking by the end of your presentation? I mean, could they be part of the standard model? Could they be any kind of interaction with it, or do you expect a new physics?
Yes, we expect new physics in this case. They may be, for example, a new vector boson from a new force, a new U1 gauge symmetry, for example, and may be also new scalars. Actually, in the same model that we have the standard scenario, for example, dark matter annihilating in some mediator producing the standard model particles, we also may have the secluded scenario where when, for example, the dark matter mass is higher than the mass of the mediator, and the interaction between the vector, these new mediator particles is teeny, we can have this kind of scenario in several extensions where that contains wind particles, for example. So it's very interesting, but usually they are mediated by these mediators are from new physics, not belong the standard model.
Okay, thank you.
Okay, just I don't have questions for. We don't have time for. Well, let's say a quick question. You mentioned that CTA may constrain primordial black holes. Is this due to the decay of these black holes, or is it a different physics?
This is a good question. Sorry, I cannot say. I cannot say.
Okay, thank you.
All right, thank you, Clarissa. So let's thank Clarissa again.
Thank you very much.
Okay, so now we have the talk by Rafael and Herman. Okay, Rafael, you there?
Hello, everyone. Can you hear me?
Yeah, perfect.
Possible? Yeah, that's okay. Good. And okay, I'm going to share my slides. Just 1 minute. Okay. Okay, I see that you can see my slides. Then I will start my talk. And first of all, I'd like to thank you all for receiving me here. Okay, my presentation will be about the signal experiment and focusing in its instrumentation. My name is Rafael. I'm from the Federal Juiz de Fora University, and I work also with Herman at CBPF and the whole signal collaboration. And we have prepared these slides together, me and Herman. Okay, so this is a small summary of what I'm going to talk today. Okay, we are going to start from a general point of view of the experiment and then try to cover also some details related to instrumentation and a few things, general things about physics. Okay, a signal is an experiment that was founded by INFN, that's a Nuclear Institute of Italy, and after it has included other international collaborators from UK, Brazil, and Portugal. So we, CBPF and USD4, we work together in many topics, going from the acquisition and trigger development of acquisition and trigger models to sensor characterization, sensor simulations, and also image processing for increasing the signal to noise ratio of the experiment in few words. Okay, so signal is a large, the objective of signal is to build a large CPC detector for dark matter in neutron studies, to drive development of new detection technology, exploring mainly the new active pixel sensors that are being available in the market. So these sensors, they are very sensitive to light, to photons, and they have high spatial resolution, and they are one of the important elements of this project. So our task is to build this detector thinking of detecting WIMPs. So we know that different models has predicted the existence of neutral particles with a mass of few GeV or higher. Okay, that would fill a galaxy, and then they could interact with the nuclei present in ordinary matter, producing actually low energy nuclear recoils that then we could detect using this kind of detector, using, for example, gas-based detector as is the TIP-C detector, the time projection chamber detector. So a general introduction. So dark matter should form a halo around the galaxy now, and then the solar system now is moving, and it's moving around the galaxy, and it's pointing to the Cygnus constellation. That's from where we got the name of the experiment. And then we expect to have some winds winds of dark matter particles hitting our solar system and hitting our planet. And other than the solar movement, we have also the Earth movement around the sun that also will give also modulation, unknown modulation of that dark matter detection. So now in our movement around the galaxy, we are pointing to the signal constellation, and then it's from there that we expect some signal to arrive to us. So one of the main objective of the signal is to measure particles, discovering from where they are coming. So we have this directional discrimination that we want to implement, and if you do so, we can uniquely identify dark matter signals that would be coming from this signal's direction. Okay, and that would be also a tool that will allow us to go beyond the neutrino floor once we have this directional information. So to observe light WIMPs, our objective is to try to discover light WIMPs, since the heavier WIMPs, the distribution have been already well explored. So we are exploring the low mass WIMPs, and for this we have to have a low signal threshold of the detector, thinking about the energy and the transfer energy that a low mass WIMPs would pass to its transfer to the detector. So for that reason, we are going to use the GAIS basic detector using helium as its basis for the low mass WIMPs. Okay, we have been studying also the possibility to use hydrogen, and we have seen that it can also have some advantage using this the hydrogen elements. So for now, the signal target is made of helium and fluorine. Actually, it's the carbon tetrafluoride. For heavier targets of because making up a heavier target for intermediate mass. Okay, and it also sensitive to spin coupling interactions. Another thing is that we are going to use low density, putting our gas in atmospheric pressure, in a way also to try to have some nuclear recoils that can have some length in its interaction. Okay, and then we can and with that we can have some information on the direction, and also if you get to build the energy profile of this track, we would have also the orientation of the WIMPs interactions in the detector. Here I have some sensitivity limits, considering a 30 cubic meter volume detector, 3 years of exposure, and a threshold of 1 keV, and also having this orientation direction identification. And we can see here these limits for 3 different backgrounds rates. So for spin independent detection, we go up under almost to 1 GeV of mass, of dark mass, and for spin dependent detection, we go under 3 or 4 GeV. Using hydrogen instead of helium, we have seen also that we can go under 1 GeV of dark matter mass. We have done some study using these guys, simulation study, and it has shown that we can go over the 1 GeV mass. So our experiment is part of a wider project that would be composed of some detector installed around the globe. Our detector itself, each one would use a different detector technology, and one of them, the signal one, is this our experiment, and it's made to be installed in Italy more specifically in the Gran Sasso mountain near L'Aquila. Okay, the signal detector concept. Then the idea is to build a TPC, as I said, detector, where the amplification stage is made of a triple jam system, where we have electron multiplication, and this process of electron multiplication generates also light. So we are going to use optical readouts to reconstruct the events by detecting this light produced in the triple jam system. So we are going to use cameras, and we are going also to use PMTs to detect these two kinds of informations. Here on the left, I have an example of an image made by a camera located in one of our detectors, and the right, the PMT signal for 5.9 keV photon event. Okay, here's the spectrum, the light spectrum that we have with this kind of technology. And the idea is to exploit the two main regions of this spectrum. The first one we exploited with the camera, where we have quantum efficiency of above 70% in this green region I have marked in the plot. And for the experiment, it's important to have good energy resolution and spatial resolution for particle tracking and energy profile reconstruction. And also we are going to use the PMT, as I said, to measure also energy, also to try to measure the z distance of the particle from the jam plane using its time resolution of its signals. Okay, so here's just one example when a particle is passing with no any kind of inclination in relation to the z coordinates, and then we have something with it has some z inclination, and then we have different signals. With this longer kind of signal, we can then discover what's the inclination of the particle crossing the detector. Okay, the signal roadmap. Actually, you have built two or three prototypes. The experiment is divided in three phases: phase 0, 1, and 2. The phase we are now is the phase 0, where we have some IND development. This prototype, we are working with it right now. And the next step then would be the phase 1, where we have a demonstrator to test the scalability of the detector, and also to study some background radiation issues. And then we go for the next and last step, phase 2, where we have a detector of 30 cubic meters to start really searching solar, actually dark matter, and also solar neutron detection. We also use it for the solar neutron detection. So from these three, let's say, the prototypes, Lemon, we were using Lemon up to the end of the last year, still analyzing data using this Lemon prototype, and now we are operating with the Lime. So I'm going to present both of them. The Lemon is a 7-liter sensitive volume. It has a jam with 20 centimeter drift distance, and its optical readout is made of one PMT in one side and a camera in the other side. So here we have the camera, we have the TPC volume, we have a jam system here, amplification system, and then we have just a black box where we can use to couple a camera at the right end of this structure. Okay, so we have got a lot of results with this kind of detector. This is some pictures from Lemon. So we have seen this is 5.9 keV photon events. We have some low energy electrons and high energy particles probably coming from the cosmic rays. And then we have the Lime. That's a prototype you are using right now. That's a bigger one. It's a 50 liter sensitive volume. It has a bigger gem foil with 50 centimeter of drift space. And for this detector, we use 4 PMTs. We have here first the TPC volume. We have the gem system in this side here, and behind the gem system, we have 4 PMTs and 1 camera that should be positioned in this region here. We have 2 prototypes in operation, one in Frascati, Italy, overground, and another one already working underground in Gran Sasso. Okay, so these are some pictures of the ground that we have took with lime, just to show as examples, and then we go for the phase 1 after testing lime, and now we have a lot of work to do with the lime prototype, but then afterwards we go for phase 1 to do a kind of detector that we use 4 lime modules using at the end 4 cameras and 12 PMTs to read out a bigger volume, TPC volume of the detector. And at the end, we have, our goal is to achieve this detector here, where we have many models of this type, and to reach 30 cubic meters detector. Okay, the acquisition system, we have those 2 main kinds of sensors, the cameras and the PMT. The cameras, we are using practically everything coming from the market. There are commercial solutions. You can read the camera using frame grab or USB ports. And then we have the PMT signal that should be also acquired. And for that, we are actually proposing a custom solution that should be developed at CBPF. At the end, we have a computing system using GPU for imaging processing and trigger decision. Okay, so we have defined also with some lab measurements the minimum sampling rate that we should work for the PMT model. So that would be something like 500 megasamples per second. Okay, the current acquisition and guide system, they are based on USB for the readout of the cameras, and also VMA and E modules for the PMT and trigger logics. We have also a control system based on MIDAS. That's a package, that integration package for slow control system and monitoring. And we use it for this proposal for the whole apparatus to have the remote control of the whole system. So the PMT custom readout model would be something new that's being developed at CBPF. That would be made of 8, one model would be made of 8 fast ADC converters, AD converters, no? One FPGA, and some connections, some external pinouts for trigger and other purposes. And also the external communication would be made with gigabit Ethernet to reach up to 3 gigabits per second of communication transfer speed. Okay. Also, we have a new trigger custom model that was sent to Italy. It's already implemented. This was also done in CBPF, and it was done for the line prototype, and it has some interesting features as Ethernet connection for remote configuration, and the FPGA firmware can also be remotely updated. The Ethernet connection itself is also very important because our experiment can be all controlled remotely, and even us from Brazil, we are able to do some shifts to help the experiment to do the data take, the needed data taken. Okay, the optical sensors. As I said, we have a PMT and a camera. The PMT we have selected 4 kinds of, actually three kinds of three models of PMTs, one of silicon PM, and we have tested with a source of light of laser pulses. We have injected some laser pulse of 6 nanoseconds, and we have measured the width at the width of the signal at the output of the PMTs, of the sensors, and also the jitter of each one of them. And as you see, the selected sensor, he has the same time of the same light, the same signal duration of the light, which is arriving. It's a cathode sensor, and also it has a small jitter of 0.5 nanoseconds. We have also tested for linearity, and as you can see, the PMT follows very well the source light in duration of time for the proper sampling rate of 500 megasamples per second. Okay, the cameras, by now we have tested also 3 different cameras, 2 produced by Hamamatsu and 1 produced by the BSI Prime. As you can see, the fusion has the lowest without noise, the largest activity area keeping the same pixel size. The flash has the best dark current, right? And the BSI, the best quantum efficiency, okay? Lemon has used the flash sensor, and Lime is using now the fusion. We have tested it. We have, for example, results of its IMS noise for each one of those cameras. We see that the fusion has the best performance for the IMS noise. We have also tested the sensitivity of each camera, and we see the fusion has the higher sensitivity followed by the CMS, flash, and the BSI can work in 2 different modes. That's why I have it here twice. And as you can see, the CMS mode has a best sensitivity compared to the ATR mode of the BSI chip, the BSI sensor. We have also tested it for the fake clusters energy distribution. And when you have only electronic noise from the sensor, and if you send it to the clustering algorithm that we are using in the experiment, you can have fake clusters that can mimic some kind of particle. And then we measure the energy of this fake cluster, the distribution of energy of these fake clusters. And as you can see, this fusion in the CMS has very low energy fake clusters, and would be occupying so a low energy range of the spectrum of the experiment, which is interesting for the experiment. So the flash and the ADR sensors, they can have fake clusters with energy as high as 1 keV, and that would be worse for the experiment to have this kind of sensor. Since we are very interested in exploring the low energy range of the detector. Okay, the reconstruction algorithm. So the motivation is just for part 1 identification. So if you can reconstruct the clusters, we can get important cluster information as energy, energy profile, energy density, and also some spatial measurements of the tracks of the clusters. And with that, we can differentiate between the different particles that are interacting with the detector. As for example, the most important for us is the nuclear recoil events. The reconstruction algorithm is made of a preprocessing system that's made to increase the signal-to-noise ratio of the images. It is sent to a clustering algorithm. We have tested 3 different kind of clustering algorithm, and then from the cluster output, we then can extract some features that can be used for event selection. Here I show some results that we have got with the 3 different clustering algorithms. Actually, NNEC and DB-Scan, they are very known algorithm for clustering. DB-Scan is based on density information, so it's always trying to reconstruct cluster regions of the image that has high density of events. And we have also proposed a small modification of the DB-Scan that we call the IDB-Scan to try to improve its performance. Okay, so here I have the results that I can compare IDB scan with NCC and also compare IDB scan with the DB scan itself. And what we can see for electronic, we have three kinds of measurements here. We have electronic noise, we have natural radioactivity, that where the detector is working, but we have no radioactive source pointing towards the detector, and have the natural radioactivity plus iron 55 photon source that we use also for characterization and other important characterization of the detector. As you can see, when you use the IDB scan, actually we have a reduction on the noise background of the detector for the low energy range below, let's say, 10 keV. Okay, so this made us to use the IDB scan as a solution for the clustering of the detector, the images produced by the detector. That's one example of its outputs. There was still one problem remained when we proposed the IDB scan, and we can see here that the long tracks, they are really still being split in many other clusters, and this also somehow makes the like worsen the signal to noise ratio in this region here, because many of these particles actually come with low energy above 10 keV, and then we can pollute this low energy region of the acquisition, the acquired images. So we have proposed another modification of the DB scan where we can measure directionality of the tracks. So we use an algorithm known as Hansaki. That's a procedure, a robust procedure for fitting. And if you find out that any cluster has some directional components, we then try to fit it with a third order polynomial fit, and also try to recover all the other elements that would make part of the cluster, of the main cluster of the image. Okay, with this new proposal, we see that we could reconstruct in a better way the long tracks, which normally are produced mainly by cosmic rays. Okay. Here I show some of the improvements we had when you included this directional component of in the clustering algorithm, and we can see here that we have a considerable reduction of background noise coming from natural radioactivity source. Okay, and we don't lose any kind of radioactive any kind of event that was produced by the radioactive source. So the efficiency of the iron 55 events are the same, but we have a considerable reduction of the noise backgrounds produced by natural radioactivity. Okay, here we can see that we can have a reduction of by a factor of 4, depending on the range we are evaluating. Okay, so that was another implementation that helped the experiment to increase its signal to noise ratio related to the images, the produced images. As those long tracks, then actually they came out from the low region of the events, and they jumped to the higher region above 20 keV. Okay, so we have for us it's very important to have this region below 20 keV as clean as possible, let's say. So since once you have all the clusters reconstructed properly, we can then measure different features and use it to separate different kind of particles. For example, here I have nuclear radioactivity against nuclear recoil events against electron recoil events, and we can see that sometimes we have a big difference in distribution depending on the parameter we are evaluating. Here we have the cluster length. We see, for example, that the cosmic rays, they have very long cosmic rays. We have the cluster width that's related somehow with the diffusion of the detector, of the actually the electron drift that happens in the deep sea volume of the detector. And this can also be used for selection of particles, of specific particles. We have two other examples: the energy itself of the clusters, and also the energy variation along the cluster trajectory. Okay, I also want to talk a bit about the detector characteristics. We have done some. I will show the main results we had with the prototypes that we have constructed. First of all, the linearity in the energy resolution. We have tested it for different radioactive sources, going from 4.5 keV to 35 and over, actually here up to 35 keV. And we have seen that in this range, we have a very nice linearity response of the detector. Okay, that will be the energy of the radioactive, will be the values that will measure with our detector. Okay, so we have a very good linearity, and also we have a very nice energy resolution of 13% when we measure the energy of these particles. 13% are almost constant for any energy range, any energy from this range from 4.5 to 45 keV.
Well, can you hear me?
Okay. Yes.
Just to let you know that I have 5 minutes.
Okay, I'm finished. So also we have done some analysis on the high energy electrons for tracking and fiducialization, and depending on the distance of these tracks from the gem plane, you see that this one is 18 centimeters far from the gem plane, and this one is only 1 centimeter from the gem plane. The diffusion we can be seeing between the difference between these two tracks here. The diffusion is bigger when you are far from the gem plane, and then we can use this diffusion information to measure actually the distance on the Z plane that the particle has interacted in the detector. So we have seen that we have using this technique, we have 15% of resolution for measuring the position on the Z plane when a particle interacts with the detector. We have also tested the efficiency for nuclear recoils against iron 55 events, which are those 5.9 keV photons that interact with the detector. We have, for this test, we have used only two discriminating variables, the light density and the PMT signal, the time of threshold actually, and using these two discriminating variables, we reach a 40% efficiency of nuclear recoil when we set the background rejection to 96% on the photon events, the 5.9 photon events. So here would be the different signal efficiency for different energy levels. And for 6 keV electron recoil, we get something about 40% of efficiency. Okay, the idea also is to include other variables in this kind of analysis, but by now we have used only two, and we believe that using more variables we get a better result. Okay, LIME has been installed underground in the beginning of 2022. So we have done the first data taking of the experiment underground. It's located, here is the infrastructure under the mount, the Giransasso mountain, and we are located here, not far from the Dama, for example, experiment. And we have already an automated system working underground, and everyone can help on the shift and control and monitor the detector, which is installed in two kind of containers. So we have one structure of 2 floors, one for the detector, one for the control system, the control room, to operate the detector. The first data take has happened in 2022, and we are now getting prepared to the second data taking for 2023. So that's what I wanted to show. I have a small summary here, and the signal experiment has given important steps to achieve its goals. The detect concept, we believe that's validated. We have many mechanical and electronic instrumentations activities done to make it possible. We have the reconstruction algorithm in the remote control system that's available for everyone in the collaboration to work with. I didn't talk nothing about the simulation, but the simulation is in a very advanced stage, and they are simulating every aspect of the detector, the signals, the background particles, and they are simulating the detector itself, the shieldings, and also the electronics. And they have many results that have been shown in different places. And finally, we have this LIME detector operating on the ground, and we are preparing for one new year of data taking for this year. So that's all, and thank you all.
Thank you, Rafael. I also remind you that Herman is author of this work, so the question can be made for you, right? So, any questions? I have a question for Martín. Thank you for the talk. It's really amazing how much things have gone on since the first. The last time I heard about the experiments is really amazing. So do you have an idea of the timeline? I know there is a lot of R&D to come. Kind of a broad idea of when the full experiment would be online?
The full experiment, the last, you mean the last, the full detector, no? With 30 cubic meters of volume. We have our plan actually is to have it. I have here the roadmap of the system. I come back to it. So you are planning, yes, more near 2030, I'd say, to have it in operation, just to give an idea. Okay.
You mentioned the clustering algorithm to identify the tracks, right?
Right.
Did someone try a machine learning algorithm for that?
Yes, but we don't have concrete solutions by now. We ourselves, we are trying. There is also another researcher that also have presented some results using artificial intelligence or neural network, for example, algorithms. But by now, we don't have any concrete results, let's say. But we have this idea to use it for the clustering and also to increase the signal to noise ratio of the experiment in a general way.
Right.
Okay.
Okay, so more questions on the remote? No? Okay, so no questions. Martin have no other questions. It's so this is a large collaboration, and I know Herman and you are involved in it. Is more people in Brazil involved, and are you seeking more people to get involved, both in the development, but as well in other aspects of the project? I mean, that's something you're seeking, like more Brazilian global involvement in that?
No, I believe the collaboration is open for new participations. I mean, in general, because we see that everyone that's coming and try to get and make part of the collaboration has been well accepted in the collaboration. So recently we have, for example, Unicamp. It's not here. I believe Unicamp is in the first slide, that has just entered in the collaboration. And for sure, that would be nice to have other participants. Now, there are many things to do in different, in varied different activities.
So more questions? No? So I think we can, thanks again, Rafael and Hannah.
Okay, thank you.
Okay, so now we have our first break, our break of the day. And then we come back in 30 minutes, right? So see you.
Hello, everyone. So I'm here to talk about how we can promote also particle physics in Brazil.
All right, so let's continue our session of the afternoon with the two last talks of the day. And after that, we have the roundtable. So we have João from CBPF. When you have 5 minutes left, I'll let you.
Okay, thank you, Martin. So, hi everyone. I'm João. I am a graduate student here at CBPF. I'm currently supervised by Professor Martín Makler, as he said. So today I'm going to show some of the results of the modeling of gravitational lenses, and especially discuss how can we use these modeling results to set limits on dark matter. So these are a few contributors to this work. So before I continue, what is strong lensing? So this is one possible configuration of strong lensing. So we can have a massive object that I'm calling here as a foreground galaxy in the context of a galaxy scale strong lensing. So we have a massive object that, according to GR, to general relativity, it will distort the space-time, and then the light from a background object, I'm calling here as a background galaxy. So we call this, the redshift of the lens as ZL, the redshift of the source ZS, and this is the kind of image that we get. So we have the multiple images. Depending on the shape of the source, we might have arcs. So, but this is a cartoon. So here we have an example of real strong lens systems. So they look really beautiful, but the key point is that these kind of events are really rare. So, and in fact, this sample is actually one of the most, the better sample that we can get, because especially most of these systems were obtained throughout the Hubble. So, okay, so just to give you a bit of context. So this is one of my favorite next generation survey, which is the LSST or Rubin. So here we have a few numbers for this survey. So it will be almost 15 terabytes of data per night. For the 10 years, it will cover almost 40% of the sky. It will be tens of billions of objects, and each one observed approximately 1,000. So here in this chart, we have a prediction of the number of strong lenses. So in blue. So and also the man-hour required to find this kind of objects. As I said, they are really rare, but in the next generation, we are going to have about this number. So this is a map of the different contributions of this the LSST, and the key point here is that one of the science in-kind contribution is actually dedicated only for the strong lens. So there might be a consensus of that of the importance of the strong lensing, especially for the next generation of surveys, and also the areas of interest in cosmology. So this is a picture of the SST. Is a giant robot telescope that will point to these systems, to different kind of objects. So bringing the strong lensing context to this meeting. So large, as Marco said in our previous talk, the large-scale structure predicts a regime of the dark matter that goes with this behavior of 1/r to 3. But however, we have so just to give a context. So we have this paper that models a subset of strong lenses using two different profiles for the matter, one for the luminous matter and also other for the dark matter using an FW profile, which is given by this equation. So the point is that we have a special scale which is given by in this region where we have a behavior of 1/r². So and this kind of behavior translates into the isothermal mass profile. So the question that I'm going to address here is, can we recover this kind of behavior from using a general power law parameter with a varying slope? So can we, are we able to recover this kind of behavior of dependence on the R? So this is the outline for this talk. I'm going to show, discuss about the modeling. So the method for the lens light subtraction that we used, the modeling pipeline, also show the modeling results and discuss a few special cases. I'm going to speak very briefly about the proposals that we made on the last year, and also discuss how we can break the degeneracy of the of these modeling results using the velocity dispersion for this obtained by the spectra, by the analysis of the spectra that we obtained throughout the proposals, and how we can break this the degeneracy of the modeling using this kind of data, and also show the results of the power law and discuss some future work. So it stopped working. I'm not sure how. Yeah, okay. Okay. So this is the data that we have, and it's actually a subsample of large sample that is being actually compiled by Renan Oliveira. So this is the idea of the kind of database that he's producing. So we'll have a website that where we can search for strong lenses and also obtain relevant parameters such as the redshifts, magnitudes, and other kind of interesting parameters that can be used. So these are a few systems that's in our sample. So, but before we start to talking about the modeling, so we have an important step, which is the lens light subtraction, because we want to subtract the lens light to highlight the arcs and also the multiple images, as we can see here, and also to identify these multiple images. So we have at least two methods to do this kind of subtraction. We have the more benchmark one, which consists in a two-step modeling procedure, where we initially have an automated modeling, an automated mask to mask the arcs and also nearby satellites. So by using this kind of mask, we model the lens light profile, so we can get a more precise mask. And then we perform again the modeling of the lens light. So comparing both results, we have a very nice improvement. This is the benchmark kind of method, but we also have another which consists in when we have this kind of situation where we have an overlap of the lens light brightness with the multiple images, we model every important multiple image or object in the cutout. Cutout is it's actually this kind of image. So we model every object and then subtract only the lens. So for both methods, we use this kind of brightness distribution, which is called SASIC. And we also have a normalization factor. So this is extremely important. So even though we have a more benchmark approach, we also analyze each system in an interactive process. So here we have a demonstration of this kind of interaction process. Here we have the chi-squared, the reduced chi-squared evolution throughout the number of interactions. So we have considerable improvement towards this kind of modeling. So we try different profiles, also try different masks. For example, we change the kind of image that we are masking, model, and then try a model. So it's very interactive process until we get reliable results. So for the modeling itself, we use pixelized source reconstruction, which is basically a map of the pixel positions in the source plane in the data, which is in the lens plane. So we have an operator that acts in the pixel positions in the source plane, which is given by this illustration. So this is this kind of operator or matrix, which is consists in a blurring effect, which depends on the atmosphere, depending on if it's a ground-based telescope or instrument. It also depends on the lensing contribution, which depends on the parameters of the lens and also the mass potential. So we have also another terms to prevent unphysical fluctuations, but I'm not going to dive into every detail. But the point is that this is the kind of examples of the lens reconstructions. So and this is a procedure of the modeling on a simulated data with a simulation of a collision or interaction between two galaxies. So and this modeling is it's done, and then we reproduced the noise observation data, and this is the reconstruction of the source using this kind of approach. So even though we have loss of information, we still can recover some interesting features of the morphology and also other parameters. So this is the pipeline that you use to model these strong lenses. So we begin with the benchmark approach to the lens light subtraction. We have, as I said, two phases, which is actually represented here. We also have, we actually begins our pipeline, our mass modeling pipeline by a source parametric section, which consists in mapping the parameter space to get a better guess of what the mass distribution parameters best fit will be on the other sections. So for this source parametric, we use a static profile, which I already showed in the other slide. So we begin with the source inversion, which I show in the previous slide, by fixing the mass distribution with the with priors of the source parametric session, and then we vary the source reconstruction. And the second phase, we do the contrary. So we fix the source reconstruction and then accommodates the lens parameters. So we end our pipeline by modeling using a more generic power law with a varying slope, which is given by this alpha. So in all these cases, we model the mass also using a shear component, which is illustrated by this by this figure, which has this kind of shear on the arcs. So this is the pipeline that you used, and these are the model reconstructions. So I'm showing here from the left to the right. The landslide subtracted image, the model reconstruction in the lens plane, the residuals, which is a subtraction between both, and also the source reconstruction. So this one is actually one of my favorite modelings, which is this one here in the upper panel, because it reconstructs a more spiral shape galaxy. So in our group, we discussed about the possibility of this kind of galaxy at this redshift with this length. So this is something that we are going to address in the next analysis. So this one is also interesting because we a residual image shows or highlights this kind of cosmic ray event or a muon, not sure. So this is important because basically it tells us that the model is not overfitting. So it's a good feature of this kind of modeling. We also have a candidate of a quasar. So I'm showing here. So very interesting aspects on this kind of modeling that is going to be discussed in the next as a next analysis. So we also have a few candidates of double-lensed sources in our sample. This is one that we initially thought about it. So and we searched on the literature about this system, and we found that it is actually a confirmed double-lensed system. So its main deflector is this G1 galaxy, and these other two are kind of a perturbation on the lens potential. So this kind of analysis is carried out by the analysis of this of the spectra and also the redshift value. So yeah, so this to model this kind of systems, we proposed a small variation of on the pipeline, which includes both kind of profiles. So I'm not going to give any all the details, but here we have the modifications. So here we have the landslide subtracted image. Here we have the model reconstruction, and also the residuals and the lens, the source reconstruction, the pixelized source reconstruction, which gives this more compact, with this more compact shape. So this paper has a measurement of the velocity dispersion, which is represented by these bar. So here we are comparing our results after the last source inversion phase and with the last mass total session. So we have a very good agreement at 1 sigma. As I said, we have other candidates for double lenses, which we also model using this the last pipeline. So very interesting that. So okay, so in the modeling we have very much degeneracy in this kind of modeling. We can discuss this in the question section, but the fact is that we have a lot of degeneracy in the modeling. So one way to break this kind of degeneracy is to have other measurement of the velocity dispersion. So motivated by this kind of application, and also to test this kind of procedure can be used to test other modified gravity theories. So inspired by this kind of applications, we decided to propose to SOAR, which is a Brazilian telescope. So we decided to propose to SOAR to get spectroscopic data of our systems. So here we have our 23 gravitational lenses, and also we aim to get velocity dispersion measurements and also redshifts. Here we have a picture of the SOAR, which is located in Chile, I guess. So this is the kind of spectra that we might get. So here we have this horizontal line, which can be understood as the lens spectra with the absorptions here on the vertical. So I think you might not be able to see, but there is actually a faint horizontal line right below this main one, which is the source spectra. So by reducing this kind of data, we can get the more familiar spectra. So by analyzing this kind of spectra, we can get also a few interesting parameters, such as the stellar mass, the redshifts, the velocity dispersion. And in fact, this kind of analysis is being carried out by Eduardo Cipriano, who presented earlier, and also his master student, Ingrid Belotto. Okay. So we also decided to propose to Gemini. There are a lot of interesting features in this system that I'm not going to discuss. So now we have both measurements, the modeling velocity dispersion and also the spectral velocity dispersion that we got from the proposal. So as I said, we have a lot of degeneracy from the modeling results. So this is the velocity dispersion, the radial velocity dispersion expression for the modeling. So using these ingredients, we can obtain this equation. But I remind you that this is not the velocity dispersion that we measure, because this is the radial velocity dispersion. Actually, what we measure is the projection of the velocity dispersion in the lens plane, and also weighted by the brightness along the slits that we got this spectrum. So this is the kind of calculation I'm doing here. So after a few cups of coffee, you can get this equation, which is not important in this presentation. So okay, the pointer is not working again. So okay, so by having these two velocity dispersions, we can build our Bayesian objects, which is shown by here. Actually, I'm missing a minus sign right here. But okay, so we have our two measurements of velocity dispersion. So we have our ingredients, and now this is these are the results that we get yesterday. Actually, yesterday. So very. But okay, so this is the result on the slope parameter, which is very. There is an agreement of with our prediction or prediction of the simulated kind of feature that I showed earlier in the beginning of the presentation. So we have an agreement. Okay. So moving, this is our future work. So we want to improve our mass and light slopes because we model the mass distribution and also the brightness distribution. So we want to use these kind of priors in our estimations. This is something that we are still not doing at this point. So we also want to replace the aperture weighting function, which is given by this omega here. We are still using the slow one aperture weighting function. This is an ongoing work. we also want to verify the effect of the automated modeling in the posteriors, if it improves our posteriors or decrease the accuracy. So this is something that might be interesting to look in the future. And we also want to dissect a few strong lenses in our sample. I'm listing 2 of them in here, but I'm sure there are a lot of interesting cases. So yeah, pretty much it. I thank you, and I'll be happy to take questions. Thank you.
So we have time for questions. From online, if you want to ask questions, just unmute yourself. Okay, so I have a question. Oh, there's a question by Arthur. Yes.
Hello.
Hi,
Can you
Arthur.
hear me?
Yeah, perfectly.
Thank you, João. I would like to understand what kinds of degeneracies can there be in modeling?
Yeah, sure. Okay, so I can speak at least at 2 different kinds of degeneracy, right? So the first one is that consists in the fact that we are modeling the mass density profile in the projected lens plane. So this introduce a kind of degeneracy in this process because, for example, imagine that you have a high complex mass profile in the 3-dimensional space and another low complexity model. So you can have this situation where you have these 2 profiles projected in the same way in the lens plane, right? So this is one kind of degeneracy. Another kind of degeneracy is actually related to this ratio of the cosmologic distances. So you have a lot of solutions for different ratios for different values of the distance that can give you the same ratio. So this is another type of degeneracy. There are a lot of degeneracies in strong lensing, but this is the kind of degeneracy that I'm talking about here.
Other questions?
Thank you.
Okay, I have a question and comment. So you were able to measure the slope of the mass, the density profile, which is close to 2, with this ground-based data, right? And a lot of results with lags, they've been done with HST data and a lot of systems. So how do they compare in terms of systematics and statistical errors? And actually, I would like to know from where you compute the systematic error.
Okay. So I think I will begin for the second question. So the systematic error is basically, which is given by here, right? So it's basically the variation of the cosmological parameters for the density for this ratio of cosmological distance. So for example, use a measurement of using the Hubble from supernova, for example, and also using the Hubble H0 for the Planck results. So by using different kind of combinations of density of H0, we can run this kind of procedure many times and see which is the variation on this kind of parameters. So this is the kind of systematics that I'm showing here. So which is the first question?
How this compares with the space-based results?
Okay. I think this kind of comparison we will actually translate in the PSF, I think. So in the ground-based measurements, you might get a PSF, which has a more elongated shape. So I think this kind of uncertainty will be translated in the PSF, but I'm not sure how we can map this kind of uncertainties in the in these kind of level of contours. So this is definitely something that we are going to do in the next procedure.
Thank you. Other questions online or from the auditorium? So if there are no questions, we can thank again João. And last but not least, we have Aníbal from San Martín University. Actually, if you notice, one of the logo of the meeting is limit from microlensing, which is one of the most direct limits on very massive dark matter like primordial black holes, but there were not so far talks on that subject. So this is the only and one microlensing talk of this meeting. So Aníbal, whenever you're ready, you can start. And when you have 5 minutes left, I'll tell you.
Okay. Hello, everyone. Thanks for having me. Let me share the screen. I'm sorry, spoilers. Can you see the slides?
Yes.
Okay. Okay. Well, my name is Aníbal Varela. I'm working in the University of San Martín in Argentina. And today I will talk about the detection of dark matter through gravitational lensing. And as Martin said, especially with microlensing events, that these events are a phenomenon that happens when a massive object, like a black hole, a planet, a star, passes through the line of sight to a luminous source, like a star or a galaxy, for example. The way to detect this phenomenon is through the increase and dimming of the brightness of the source star. In this picture here in the left, you can see that, for example, a lens, when passes through the line of sight of this observer in Earth, when the lens passes through this line of sight, the photons that normally don't go to the Earth deflect by the gravitational lensing, and that cause an increase of the detection of photons, and so the brightness in time. So this is the way to detect these events. So a little bit a story. In the 1990, there are the people think that the dark matter could be formed by baryonic matter, like black holes, neutron star, white and brown dwarf, for example. And they call them machos for massive astrophysical compact halo objects. And in 1986, this person here, Bohdan Paksinski, proposed in a work that those candidate for dark matter could be measured with microlensing. Okay, but in that work, he also make a forecast for the probability of detect one of those events, and that probability is was very low. Is of the order of the 1 × 10⁻⁷. So this means that one have to monitor millions of stars to see one of these events, and in that time is something that can be reached for the technology, but now it's possible. Now it's possible, and there are a lot of limits in dark matter put with microlensing. For example, this is a parameter space for the fraction of dark matter that could be primordial black holes. And this plot shows the 95% of confidence level for the fraction of dark matter that be in form of primordial black holes. And so this whole area in white is the fraction of dark matter that can be found in this candidate form, and all in here in shadow, in this color shadow, are refused to be a fraction with 95% of confidence level. And here this plot here is the same here for microlensing, and this is all the collaborations that collaborate to make these limits: Hyperspring, Ogle, Eros. Okay, so what is the way to obtain those limits? One person who want to make who puts limits in that way needs to compute event rate, and that is the distribution of duration of microlensing events. Also, one needs to compute the efficiency of the telescope that want to use to detect those events. With these two ingredients, one can calculate the number of expected events, and then he must observe some events of this kind, and with all this, one can compute these limits. So what is this event rate? And before to understand what is the event rate, one concept that is key in the microlensing theory is the optical depth. That is the probability of having an microlensing event in some part of the sky. Here in this plot, we can see the optical depth in function of the distance in the direction of the large Magellanic cloud. We can see that the probability of having an event augment with the distance. That makes sense because we cover a larger area, so the probability that one lens pass through the line of sight is higher if we make the line of sight bigger. Okay, and this is here the expression for the optical depth. The function relevant here is the mass distribution. For example, if we look into the large Magellanic cloud, this mass distribution is the mass distribution of the halo of our galaxy. And there are other parameters like the distance to the source and distance to the lens. Okay, so the event rate, or the differential event rate, that provides the information about the rate of occurrences of microlensing events as a function of their durations, that is these plots here, is computed as a double derivative of the optical depth in this way. Here, this time is the Einstein time, the time of duration of the event, and this is the time of observation. Okay, so with this plot, we can compute for a given distance and a given distribution, mass distribution, how many events we will see with a certain duration. For example, this plot also is for the Large Magellanic Cloud. And we can see that, for example, with a duration of, in this big cube here, for a duration of 10 to the power of the -2 days, we will find this quantity of events. For example, one event of 0.01 solar masses. Okay, with this and the efficiency of our telescope to detect microlensing events, one can calculate the number of expected events. The efficiency is the probability to detect one event, and is obtained through simulation that takes light curve simulations that take into account the cadence and considerations such as the limiting magnitude, weather, observation gaps. And with a detection criteria, one can estimate what is the probability for detect a determined event. And this here is that function. Okay, with all this parameter here is the exposure. With all this, one can calculate the number of expected events. Here, we can see the efficiency for the macho collaboration. That was one of the first collaboration to look for these machos candidates. And here are the expected number of events for this collaboration. Okay. Once we have all these ingredients, with the observation of some event, we can put this limit. For example, in this plot, these areas in red shows the exclusion limits for the HSC observation. That was a one-night observation for microlensing events, and the EROS survey that was a survey to that monitor the Large Magellanic Cloud. HSC monitor the Andromeda galaxy. And this is the exclusion limits that they obtain with the way the algorithm that I explained. For example, errors don't detect any event and can put these limits. Eros look into the Large Magellanic Cloud in the same way as the Macho collaboration did. So since they don't detect any event of these machos or primordial black holes, the procedure is the same for these two candidates. The exclusion limits that put Eros are more strong than the ones that put macho, the collaboration macho. And macho detect 17 events. So if we can look at the way that one can put events, we can see that we must calculate this exclusion limit first, assuming that the events are generated by the boson distribution like this, assuming that the dark matter fraction that can be primordial black hole or machos is the mass, the function mass for primordial black hole over all the dark matter. Then the expected number of primordial black holes or machos is this fraction. The number is expected is a fraction of the total number of expected events. We then find this region asking that this conditional probability is 0.05, and then we can make these curves. Okay. So in blue here, we compute this forecast, if you want, for the LSST, the Large Synoptic Space Telescope, the Vera Rubin telescope now, and with a flat efficiency, and we obtain the limits that Vera Rubin can put over these candidates. Vera Rubin is not operating yet, and it will be the next year, but we can say something now with this procedure. Okay, still here. Something more about this procedure is that it's not only for machos or primordial black holes. Can be used to put these kind of limits over another type of candidates, dark matter candidates, such as boson stars or axion stars. For example, here I let two references to limits put in boson star, that is these plots. For example, these first three plots, we can see the limits put for extended structures, but with the Navarro-Frank-White mass distribution. And here in the last plot are the exclusion limits for boson star, put with a mass distribution for boson star. Other kind of studies like this also put limits on action stars, like this work here that I let the reference. And also there are other studies for microlensing that put limits for primordial black holes, for example, forming clusters. And I let a reference here too. So finally, microlensing can be used in other searches, like the detection of planets, like free floating planets that are planets not bonded to any star. And well, also for the planets bonded to a star. Here, for example, we can see light curves for a planet not bounded, a free-floating planet. The light curve is associated to 1 point source and 1 point length. Other effects can be considered, but then for this talk, that's enough. And also here we can see a detection, for example, for a bounded planet, a planet bounded to a star, and we can see that this light curve is similar to the light curve associated to a one lens, but with a peak, one lens that here up it's a planet, like I said, but here this light curve is a star, and this peak it's a planet. So okay, microlensing can be used to detect planets, bounded and not bounded. And that's it. That's all I want to tell you. Thank you very much.
Questions to Aníbal? So questions from online participants. If you want to ask, just unmute yourself.
Hello, Aníbal.
Hello.
Hello, thank you for your presentation. Can you explain to me a little bit more how to obtain the efficiency and the exposure?
Yes, the exposure, it's a parameter of the telescope. It's the number of stars that you see in a given time. And the efficiency, for example, in this is our light curve simulation that we are making with Martin for a project in the Vera Rubin telescope. And another telescope that we'll send in a few years. But these kind of simulations of light curve simulations allows you to study what kind of events you will be able to detect with your telescope. For example, these points in blue have a very wired cadence because you have these seasonal gaps. Can you see it? These gaps with no observations. And if you have events with a low mass, that means that the duration of the events it's very low. Can be that you don't detect any of those events because these events drops in these gaps, in all these gaps. So your efficiency will be very low. That makes some sense to you?
Yes, sure. Thank
okay,
you.
that is a way. So you make a big light curve simulation, a big set of light curve simulations, and then put a detection criteria and detection criteria for the events, for the light curve. And your simulation of the light curve will contain all the photometric properties and the cadence of the telescope. So when you combine these two things, the detection criteria and the light curve simulation that contains all the properties of your telescope, you will find what is the probability of detect some of this event that you're looking Okay.
Okay, thank you.
You're welcome.
More questions?
Aníbal.
Hey.
Thank you for the talk. It was really interesting. I was wondering, do you use, I mean, for the estimates for LSST, do you use some of the LSST infrastructure? So are you working already with LSST groups or science collaborations?
Yes, yes. All these light curves that you see now have the cadence for LSST and the limiting magnitudes, and these light curves in blue are have the cadence for the Roman telescope, and also the limiting magnitudes, the photometric parameters associated with the telescope. So yes, this is a realistic light curves.
That's really nice. Thank you very much.
You're welcome.
Perhaps just to clarify for Nelson's comment. So these light curves, the last ones that Aníbal are showing, these were produced within a project for the microlensing working group on LSST. So as Aníbal say, they are very realistic, using the data products like the OpSims and error models and so on. The constraints, the forecasted constraints on the exclusion limits on dark matter, this is different. That was a thing of a project. So those, they use a very rough estimates on what the efficiency is for the detection, both for M31 and for the LMC. So this is one of the things that Aníbal will revisit now that he has a lot of tools, including tools to identify the light curves. So now he can make very extensive simulations of light curves and use a light curve classifier to really measure the efficiency of the detection, which is one of the terms he explained in the integrals. So those exclusion limits, they can be revisited. And also,
Yes, Nelson. These exclusion limits are not realistic at all. We consider here with Martin a flat efficiency, so this is not okay. But
right. But
okay, with these simulations, we can compute a more realistic efficiency and put these limits in the right way.
Excellent. Thank you very much.
You're welcome.
More questions or comments from the audience or from online? Okay, if not, let's thank Aníbal again.
Thank you.
Okay, yes. So for all those that resisted, not so many, after 3 very intense days of dark matter meeting, I think we are ready to make our closing discussion. So the slide will show up, I guess, in why it doesn't show up. Let's just say a few words. So as I said, these were 3 very intense days. We had a sort of overview of some of the aspects of dark matter detection through scientists from Rio de Janeiro and from Latin America, most from Rio, Brazil, and Argentina. Of course, there are much more. But the idea was here originally, as we know, to discuss the potential. To discuss to promote the knowledge of what's being done in the field in Rio and in the region. I think we fulfill this objective, and we really had this overview. Okay, so what's next? So that's the idea of this roundtable. It's a virtual roundtable. So for this, we'll have Nelson Padilla right now. Farinaldo has recorded his speech, and then I'll make some comments at the very end. But Nelson has to leave, so we'll start with him. So the idea is that LSST, I mean, as we said at the beginning, the vast majority of the work being done, as shown in this workshop, but in general, in dark matter comes from astrophysics, just because it's the only place where positive signals you have. And there is a myriad of observables connecting astrophysics with dark matter. Of course, there is light curves. Of course, there is emotions in clusters, the CMB, and all these classic observables that you heard. But there are many, many more in strong lensing, in tidal streams. You heard about microlensing right now. And what's interesting is that there is a wide field survey which will cover all these observables. So the vast majority of the astrophysical observables will be covered in different aspects in a single survey. And Argentina, Brazil, Chile are part of this survey. And that's what we are going to hear from Nelson now.
All right, I'll try. Thank you very much, Martin. So, yes, as Martin mentioned, I mean, there are several opportunities to study dark matter, and one that we are, I think, several people in the different countries in the region have access to is, well, will be the Rubin Observatory, right? So, and Rubin is very particular in the sense that, as Aníbal just showed, it will have quite a very interesting cadence to, for example, do microlensing searches for compact objects, right? That is one of the many possible candidates for dark matter, but it will also be useful for several other types of science, right? So, I mean, one of the interesting things about Rubin in particular is that the data will be starting to be obtained reasonably soon, right? So we, at this moment, the telescope is almost ready. The commissioning phase of data acquisition will start quite soon, perhaps in about a year's time, and there will be a first data preview obtained with the full LSST camera that should be released after a few days of first light, of the full system first light, which should be delivered by October 2024. That, of course, is data only for a few days, but as you know, the high cadence of LSST will probably produce several thousands of alerts. Not really sure how much of that will be useful for dark matter, but what will definitely be interesting is the data preview 2, which is expected less than 1 year after this date, I mean after October 2024, in August of 2025. So that will be all the reprocessed science-grade images obtained before survey operation. So I guess data preview 2 is actually quite interesting, and more interesting will be the data release 1, which is 6 months after survey operations start in early 2026. So that's only 3 years from now, which is quite nice. And just to mention some things before opening to the discussion, I was just looking at the international data rights holder, and Argentina, Brazil, and Chile are very prominent. Chile is basically a member due to the telescope being installed in Chilean soil, and Brazil and Argentina have provided in-kind contributions of different types, right? So there are people from several universities in Brazil, and also several institutes, and also universities in Argentina. So that's quite interesting. And specifically related to dark matter, we can, there are different science collaborations in LSST, or Rubin, as we call it now. And I guess, I mean, everything that is sort of extragalactic has some components of dark matter in it, right? Because, for example, looking at the LSST science book, one can identify very quickly that several parts of the work done in the in anything related to lensing, right, has quite a strong component of dark matter. For example, all substructure in lenses, dark matter substructure, that could be very interesting to find, you know, properties of dark matter, or if it is a particle, thermal origin, what is the mass of the particle, by looking at the abundance of low mass, very low mass substructures, right? Or even primordial black holes, right? That could increase the abundance of very small dark matter halos. Then properties of dark matter in merging cluster lenses, of course, with lensing, I mean, micro lensing events, and on a slightly different area of, you know, science collaboration, everything that's related to large scale structure has some influence and has a component, strong component that is dark matter, but it is not really too easy to discern different dark matter models unless they produce, for example, differences in internal properties of halos, right? On the very large scales, we know that everything sufficiently cold should reproduce observables in a very reasonable way, right? But one thing that from large scale structure that could also be interesting is related to primordial fluctuations and constraints on inflation, which could also affect, for example, the possibility, I mean, could also tell, be telltales of influence of different dark matter models, right? Also, for example, non-Gaussianity obtained via higher order moments of the distribution of matter, right? Galaxies is one, and also cosmological physics in general, right? So there are several different places in the different collaborations where people are interested in looking at the properties of dark matter. So I thought that was that's a summary, sort of very brief summary I had prepared. You know, maybe you have some further information or comments or questions.
Questions, comments? Maybe just to complement what Nelson said, if there aren't questions. So LSST has a whole, as Nelson said, dark matter permeates a lot of the different science working groups of LSST. And there is like a summary on this website. Oh, I didn't put the URL, but I think it's elsewhere. So there is a big effort to summarize what LSST can do for dark matter. And there is this website, there is a large white paper, it's 90 pages long. There is a summary for the Astro 2020 Decadal Survey. So all this is available there. And there is a very nice plotter where on the left-hand side, you have models. So many of the models we've been hearing on this meeting. Then on the very right-hand side, you have what objects we were observing. Like for microlensings, we are looking at stars. For other probes, we are looking at clusters or galaxies and how those things connect. So how the model affects the probe, let's say subhalo abundance, like Nelson mentioned, and then how you can measure these in different observables. So I think it's a very nice way of displaying the information. So it really shows how those things are, on the one hand, very interconnected, and on the other hand, how a single large survey like Rubin is able to probe all these different aspects. So I think this is, of the imaging surveys in cosmology, is definitely the most comprehensive and promising for dark matter science on the astrophysics side. Okay, any question, comment about LSST, Rubin? Okay, so I think we can go to the next speaker, which is Farinaldo. He recorded like a 13-minute speech. So again, the motivation is of this roundtable is how to foster the development of dark matter research in Rio de Janeiro and Latin America in general. We just heard about Rubin, astrophysics side, and now we will hear Farinaldo opinion on that. And then we will have like a recap of what's been done in Rio that we learned during this meeting, but also what we can do in terms of associations, of groups, and what initiatives are going on that we could contribute to. And let me give a spoiler, is that there is something called LASFARAI, which is a forum that tries to organize the high energy physics, astrophysics, astroparticle physics in Latin America, and they have opened a call for white papers. So maybe that's an opportunity to get the community together on that. So that's the spoiler, but let's play Farinaldo's talk. Pode colocar o link lá do YouTube?
Hello, everyone. So I'm here to talk about how we can promote astroparticle physics in Brazil and in Latin America. Most of my talk will be based on my experience in Brazil for obvious reasons. So I'd like to first emphasize to all of you that astroparticle physics is not common in Brazil and Latin America. It's not very popular. And the reason is simply because it's a baby. Abroad in the United States or in Europe, astroparticle physics is a very big area and very relevant. But in Latin America, it's very small. Then we have to know that. And there are historical reasons for this. For instance, in Brazil, the very first session on dark matter physics that happened in the spring meeting or in the high energy physics meeting promoted by the Brazilian Physics Society happened in 2011. So about 11 years ago. So it's a field that has 11 years of existence, basically recognized in the Brazilian Physics Society, cannot be too popular, right? So 11 years. If you take 2 years of pandemic, it's 9 years. 9 years of a field is not much. So it's our role, if we want, right, to promote this field. And the way to promote this field, in my humble way of thinking, is by organizing events, either at the high level, scientific level, or at the undergrad level. That's the way how we can really promote and engage students early on in astroparticle physics. All undergrad students, they are really familiar with astronomy. And if you ask all undergrad students who just started their studies, if you ask which field do you think is popular, which field you're interested in, and most of them will say astronomy. Well, because astronomy is common to their daily lives, and you see on really nice videos on YouTube. You can really like engage, you know what's relevant, what are the topics that people think about and talk about in science and so on. But in astroparticle physics, they think it's just a made-up name. Well, it's a made-up name indeed, but has a meaning, right? and they are not aware of. Most of them, even my colleagues, my peers, they had no idea what astroparticle physics were before my arrival. So we really have to have that in mind before promoting astroparticle physics. If we just keep organizing very high level scientific events, we will never be able to grow as a community. We'll always obviously form students, and we'll grow little by little. Once you have PG students, I have PG students, they are already graduated, they finished their theses. Sure, it will be 1 and 2, 3. That's not really growing as a community, a big boost. You have this big boost in astroparticle physics, either in Latin America or in Brazil in particular. We really need to promote events at early on. So for undergrad students, they will be aware of the importance of astroparticle physics, what are the topics which you're interested in. We are really in a national field, right? So that's very important because there are fields and lines of research in Brazil which are not really connected to an international agenda. And they are like really small bubbles where people just work with their peers that work in the different state, and they are not really try to solve an important that is relevant for the international community. It's just small collaborations between like inside the bubble. Our community is very different because it was born differently. So having in mind that these communities started around 2011, that the very first session, I would say the community started in 2011 because it was the very first session on this meeting, high energy physics meeting promoted by the Brazilian Field Society. But at that time, there were very few people, a handful of people work on something related to dark matter or connected to astroparticle physics. Most of the people who say that I work on astroparticle physics, sure, they do work on astroparticle physics, but it's related to OJ observatory. We're just probing, not just, they're probing cosmic rays, and they are not really worried about the particle phenomenon, the particle physics, like related to beyond the standard model physics or the nature of dark matter. It's just astrophysics, which sure has some particle physics and interactions involved. But in the context of dark matter, which is what this event is proposing, I'm talking to the attendees of the Rio de Janeiro dark matter meeting. So in this context of dark matter, not many. The thing changed when Fabio Yoko arrived at ICTP Safer in São Paulo, and he started promoting events in astroparticle physics. There were other people who were working already on dark matter, such as Ivone Albuquerque. She was working on a given drug detection experiments. I forgot the name. But she was just her. And once Fabio came, he started really organizing events. And that's how we started having a community involvement. And Martin also organized events, which I participated, which was precisely roughly when I arrived back in Brazil in 2018, which was the Dark Matter Neutrino School and Workshop headed by Martin, which will have a second edition next year, 2024, again, headed by Martin. And this was really started growing when Fabio Yoko arrived. And then started promoting events. There are many people who were coming from abroad and working on astroparticle physics. But as far as I know, none of them created a route in the country. They all left. So unfortunately, they didn't have many students, or they didn't build up groups in Brazil to work on dark matter. So that's unfortunate. And then Martin started really getting involved in dark matter from the astroparticle physics point of view. There were other professors from high energy physics, collider physics, such as Vitor Gonçalves, Gustavo da Silveira. There were other professors who were in the particle physics side and started becoming more astroparticle physicists and astroparticle physicists. And that creating a community, There were also Enrico Bertuzzo in São Paulo working on dark matter, neutrino, mostly neutrino, but a bit on dark matter, connecting to dark matter physics, in connection to dark matter physics. There are a few, like a handful of people who work on dark matter. So it's still young. That's why I said in the beginning, there are subparticle physics in Brazil, and it's just a baby. And even in Latin America, it's just a baby. There are very few people working on subparticle physics, especially in connection to dark matter. So that said, to me, honestly, I think the only way how we can really promote subparticle physics in Brazil and in Latin America is by organizing, promoting events, both at the undergrad level and for high school students. To me, that's the only way how you can really have increased the flux of students interested, engaged really on subparticle physics, because then you pick them up from early on in their careers. And that's to me, that's irrelevant, because if you have a master's student, most of the time they already made up their mind about the research they want to be working on. And might be a field completely different than ours, right? So to me, that's a way how we can promote subparticle physics. Fortunately, Rogério Rosenfeld is one of the persons behind this subparticle physics community that was created. And that's one of the ways how we can also promote subparticle physics in Brazil and Latin America. But we have to be really aware that it's still a baby. There's a field that's growing in Brazil and growing in Latin America is slowly, because it started, let's say, 9 years, 10 years ago, for real, related to dark matter. Related to dark matter 9 years ago. It's not much, right? But hopefully within a time scale of 1 decade or 2 decades, this will be, instead of a baby, a well-established line of research, both in Brazil and in Latin America. So that's all I had to say. And thank you so much for listening to me one more time. And just to finalize, sorry, one few sentences before I forget, I'm gonna list here at the end just some of the events that we have organized in Brazil or in Latin America, okay? Or some of the events that we organized abroad, okay, as Latin Americans. So this one was organized by Fabioco, was a school on dark matter workshop, and the training workshop by Martín Makler, sorry. There was a South American dark matter workshop organized by Fabioco in 2018. There was a South American dark matter, South American workshop on cosmology, I think was organized by Rogério Rosenfeld. There was another South American dark matter workshop organized by Fabioco and Ivone and Henrique Bertuzzo. And then 2018, that's when I arrived. And then I started organizing those events because they were around the time when Fabioco was gonna leave Brazil. And then I started organizing those events at ICTP Safer. And then I organized a school on astroparticle physics, workshop, Dark Universe workshop in 2019, another event in 2021, another event in 2022. There were a couple of schools they organized in Natal related to astroparticle physics or dark matter. We were involved as Latin Americans, we were involved in the PASCO's conference, which is really big, also in the WIN conference in the US. And so Latin Americans be involved in the organization of these really big events in astroparticle physics. That's starting, to me, it's the sign that we are now becoming relevant to the international community as a whole, right? We had also other people joining these dark matter workshop, which is also Dark Universe workshop, which is really big, such as Ricardo Sturani was one of the guys who were organizing these events. We organized three schools related to astroparticle physics and dark matter, devoted to high school students. To me, that's the way how it should go. And we had also obviously schools on high-end astrophysics. There are many. I'm not gonna go through all of them. As you can see, there's a whole list of events right here, and some of the other events right there. I'm not gonna read them all, but just to show you that we started. Okay, so it's young, less than 10 years of existence. This field of related to dark matter, but is going and is growing fast now. through those events, not just these high-level scientific events, but through events where we really try to target those undergrad students and high school students. Because then once they enter the university, this what I want to do. I wanted to do something related to particle physics and astronomy. And you combine them both, you get astroparticle physics. So that's all I had to say. Thank you so much for listening to me, and sorry for taking so long. Bye.
Thank you, Farinaldo. Okay, any comments?
Okay, thank you. First of all, I'd like to congratulate for the event. Congratulate CBPF. I'd like to make a contribution to Farinaldo's speech because I think it was really interesting what he said about the many set of areas, the many areas of physics that are studying dark matter. And it was actually one of the factors that made me come here to study, to watch all the talks, because in the website there was written that it's an interdisciplinary field. So, and I study interdisciplinarity. So I wanted to see how it is. So, and it made me think about the consequences of dark matter in the way that physics is studied, because as Farinaldo said before in the past, this is still happens, but I think that dark matter came to change it a little bit, at least, because people were closed in bubbles, as he said, and dark matter came to mix at least two or more areas. So, and not only the knowledge of, for example, astrophysics and particle physics, but the interaction of a astrophysicist and a particle physicist. So they could assemble, for example, a new subject, such as he said, astroparticle physics. So, and I'd like to talk also, I'd like to highlight actually what he said that I think is really interesting to divulgate more this area. And of course, he talked about the events that have been organized, and I think that it's a start. Also, we have to have in mind that Brazil specifically and Latin America in general are peripheral countries in terms of the economic, the world is organized economically, so it makes things a little bit more difficult to study dark matter, for example. And also there's another difficulty that is our educational systems, because it makes because we don't have the structure such as in other countries to reach more people, more students. So I think that we have to have that in mind when we think when people will think about how to reach more people, how to broaden this area, how to advance in the studies, not only in the high level, as he said, but to bring more people to study, because it would improve the chances of advancing if there are more students coming to this area specifically. But I think that it applies also to another areas of science in general. So I think that's it. Thank you.
Thank you. Anyone wants to comment on this comment or anything on Farinaldo's, on Nelson? Okay, if not, then we can go to the third part of the roundtable, which is okay. So the third part. I know I repeated this many times, but I think it's always good to fix the idea of this interdisciplinary nature of the field. We have this diagram that's been shown many times where you think there is a dark matter, right? We already had a discussion whether it's a particle or a modification of gravity. I don't think there's much difference. The only difference is that if you think of a particle, you usually think there is a way of interacting with the standard model. So chi is the mu particle, q is the standard model. And if we don't use a mediator that we know, like the photon, it cannot be the photon. The photon cannot couple to dark matter, otherwise it's not dark. If it's not Z0, so the weak interaction, the neutral current, then it has to be a new mediator. So basically, usually we get a couple of things, like a mediator and a particle, right? Of course, there can be many creative ways of thinking. That's within the usual way we think on particle physics. But anyway, so this diagram shows like, okay, in one direction, you have a dark matter decaying into something or self-annihilating to something that you measure on a high energy infrastructure like Fermi-LAT, or we heard about CTA and so on. On the other hand, you have an accelerator, which is smashing two pieces of standard model and maybe creating something like dark matter. And finally, you have something like dark matter scattering on the standard model, and you see recoil or some energy deposited on the standard matter that would be due to dark matter. So this diagram shows like the indirect detection, which is exemplified in the left, direct detection in the bottom, accelerator in the right. And of course, astrophysics, as we say all the time, astrophysics is like it appears like something apart. It's mostly gravity, and gravity is not within that diagram, but it's where there has been a lot of effort. And of course, it's what's more developed in Brazil too, like we saw in the number of talks in this meeting, right? But so let's see what we learned, at least what I learned, organizing this meeting and with other interactions. So what kind of physics it's being done in the Rio de Janeiro state connected to dark matter, right? So astrophysical probes, we heard many talks. And cosmology, we heard one talk. There are many more people exploring the effects of dark matter on the very large scales of the universe. On extragalactic astrophysics, let's think about smaller scales like galaxy scales. We heard talks from the Valongo Observatory, from CBPF. And on even smaller scales within our galaxy or nearby galaxies about microlensing. So going away from astrophysics, direct detection experiments or detection techniques, we heard about the Signal experiment, which has people from CBPF and the Federal University of Juiz de Fora. Juiz de Fora is supposed to be in Minas Gerais, but we thought of incorporating it in the state of Rio. I hope that's not offensive. We didn't have talks about, but there is also experiments that involve people in the Rio de Janeiro state. The Escura experiment is a large CCD experiment that's been prepared to detect dark matter. The M-square is also a CCD experiment, a small sort of a prototype that is operating in Argentina. And CONI is not really a dark matter detector. CONI is a neutrino detector, but uses the very same technology that people are using to detect low mass dark matter in CCDs. So if we think about techniques, surely we should put CONI there, and there is people in the UFRJ and CBPF involved. We then heard about interact dark matter, astroparticle physics, about CTA, SWGO, which is a horrible acronym, but what can I say? Auger, of course, there's a lot of people that has been working in Auger in Rio. I'm not sure about what kind of specific dark matter analysis, but we think of high energy astrophysics. Then about the accelerators, we had a talk by Murilo about LHCb searches for dark matter. And of course, if we think that dark matter is the realm of beyond standard physics, there are a lot of people at CBPF, but at UFRJ and many places, a lot of people from the theoretical particle physics side, from the experimental particle physics side, from a field theory are looking at beyond standard model, right? I'm not sure if there is people working specifically in dark matter models in Rio. That would be nice to hear. And if there is people working on viable alternatives to dark matter. So that's why it's great. But you see that even locally, and as Farinaldo said, although the field as a field is quite new, we had quite a lot of diversity in Rio. The question is, as like we put at the beginning of the round table, how can we foster the development of field, right? How to make the sum of the parts to be greater than how to make the whole to be greater than the sum of the parts, right? Okay, this is Rio de Janeiro. Thinking about Brazil, there has been this summary. Of course, we cannot read. Let's see the next. Okay, it's the same. Brazilian Community Report on Dark Matter. So if you want to have an idea of what's been done in dark matter in Brazil, there is this paper. It's 10 pages. You can read it. It was really organized by Farinaldo, although he has a lot of authors in alphabetical order. I think mostly it's his work. You can have an idea of who's contributed. You can see a lot of the people that were here, like Farinaldo, Murilo, Davi, and many others. That gives you an idea of the size of the community, of what they are doing. And this was in 1919, but already things changed in 3 years. Maybe it's time to update, to enlarge. But I mean, I recommend those that are interested in having this broad idea of the field, take a look in Brazil, take a look at this paper. Part of all that diagram that I showed before involving direct, indirect, and accelerator experiments, this physics is contained in a sort of an association in Brazil that's called Rede Nacional de Física de Altas Energias, right? So if we start discussing a little bit of kind of policies or politics, that's a place where we have to make dark matter present as such, as a field. It involves a lot of the things that are being done there, but perhaps we should put something like a tag dark matter there. But that's a place where that can be used to foster dark matter research. Then when we think about Latin America, well, I'm not aware of everything, but basically all the topics that we selected for this meeting are present as a whole in Latin America. All these fields are represented, right? An example we just heard from Nelson is Rubin LSST, which is one experiment. A lot of Latin American countries are involved, and a lot of the astrophysical probes of dark matter are involved. So we already heard about LSST. Then we can mention about a bit the associations and the events. So LSST, we mentioned that. This is the paper, the 95-page paper is a summary of how LSST, Rubin LSST, can be used to probe dark matter. Oops. So when we go out to Latin America, there is an association, very recent, very new, has been established maybe last year, which is the Latin American Association for High Energy Cosmology and Astroparticle Physics. So we don't have a tendency nowadays, maybe, to get a lot involved with these associations. People just go and do their research and get their funding. But if you want to be heard, like by governments, by higher people, as individual scientists, it's not easy. So we have to go through these associations. So if we want the association to be lively, to be useful, to be, let's say, fighting, we need to do it, right? Because these associations are made of people, of scientists. So just definitely take a look at that, because basically everything that we say about all these interdisciplinary fields of dark matter are contained within this association. So it's sort of centered in ICTP in São Paulo, because it's the South American Institute for Fundamental Research. So it makes sense, but it's for all Latin America, right? So that's a question I put to the audience about how to foster dark matter research at LA HICAP. So this this association emerged from this process, which was called Latin America Strategy Forum for Research Infrastructure, LASFARI. So this came after the realization that a lot of large and expensive infrastructures are needed and are used for research, but maybe we should try to make understand what is going on, see what are the needs, prioritize which are the more relevant experiments. So that's the idea of organizing the community. In let's say Europe or the US, there is a tradition that the community self-organizes. Of course, it talks to the government, but there is an organization feeling that the community tells what's important and the government decides what to fund, but guided by a global community. In Brazil, and I don't want to go into a lot of politics or complaints, but usually one person with a lot of power, a lot of energy, goes to the government and asks for a lot of money. And that's maybe not the most efficient way of doing good science. But I talked too much and I see Thiago has his hand raised. So yeah, Thiago.
Sorry, do you want to finish? Maybe I can comment or question later. I mean, just wanted to comment.
Some slides, but if you want to say something about this in particular, since you were part or you are part of this LASFARI, I think it's a good moment.
Yeah, so first of all, do they have another call for white papers now? Is that correct?
Yes, I'll mention that, yeah.
Okay, so I think that I'll wait for you to finish then to comment a little bit more, but just my impressions from LASFARI is I think there were a few problems there as well, and I think that's what we have to pay attention, in the sense that first I was there nominated by the Brazilian Astronomical Society as a representative, but when we try to contact people within the Brazilian Astronomical Society, since I was representing them, pretty much everyone was just very nonchalant about the whole thing, and they were not interested in being a part of it or submitting white papers. So my role there as a representative of pretty much no one was a little awkward, I would say, because there was no involvement. So if we want to go in that direction, we should certainly organize a bit more, and that was something that I could not do when I was part of LASFARI. But at the same time, a lot of people who were there were mobilizing in self-interest, I would say. So there was a big movement, for example, to include representatives from FAPESP. And of course, those were people working in Sao Paulo. And we know that FAPESP does not represent people from the entire country. But the idea was that it was an international thing. And I was trying to move to have people from CAPES and CNPq there. So it became a weird environment, in the sense that people were still trying to advocate for themselves for a large part of it. So I think you're certainly going to talk a little bit more about that. And I do like the idea of LASFARI very much, or something along those lines. I think this sort of organization, and to have some sort of contact with the government and with other spheres is very interesting. And I think that the main point here is trying to be organized. And I think that's certainly really important. But we just have to pay attention so that it's inclusive and it's organized enough that it represents well the community as a whole, which, as you said yourself, in Brazil very often is not the case.
Right, yes, very good points. I think a key aspect of all this that you point is that, on the one hand, the community doesn't have a tradition of self-organizing, right? As we both said, it's like big bosses fighting for their money usually. So that's something that's a culture that has to be created. But also another point is that in the countries that we mentioned as an example, like Europe and the US, there is sort of a guarantee. There is like it's not maybe written, but it's like a tacit agreement that the government will take this into account. So people put a lot of time in this planning, a lot of time, more than this LASFARI and so on. There is a large process in physics, which is called no mass process. There is a decadal survey in astronomy. These involve a lot of people, work, travel. So people put a lot of energy, but they know that this energy, they will have a result. An example is LSST, which was the top ranked observatory in the 2010, I think, decadal survey, and now it will start next year. So I think that's one thing that we can try to, I mean, not we, me, I think, the community, we have to try is to make to make the governments, this is governments is a plural because there are many countries in Latin America, but at least to Brazil, those we have access, or Argentina, or each country you have access to. We need to have some kind of how you say signaling from the government that they will hear the result of this. Of course, if we tell the government, we decided that you will fund a $50 billion project, of course they will not, right? We have to be realistic, but there has to be a channel with the government. If I think if we don't have some kind of feedback from the government that they will take this into account, people will not put energy on that. Of course, everyone is overcommitted, teaching, doing research, seeking for funding, and so on and so forth. So if we don't have this side, the government side, it's harder to make the community work together. So maybe one of the strategy things would be try to get either government or the FAPs. Thiago mentioned FAPESP. That's a big thing. I don't want to enter the details, but FAPESP sometimes sort of works like at the national level, but it's at the state level. So instead of FAPESP, like CAPES and CNPq, like Thiago said, of course, would be national, or there is an association of FAPES. There is an association of the local funding agencies of the state ones, which I forgot the name, but is an association of FAPES. So FAPERJ, FAPES, FAPESP, all those are part. So maybe getting this, I think it's CONFAP. Anyway, so getting this thing involved, right? But anyway, I think that there must be an effort for those that fund science that they would take this into account. Otherwise, it's hard to get people to get put their time on that. But that being said, well, why I mentioned this, as Thiago said, there is a call, a current call. There is a current call for letters of interest. So this process is continuing. The mapping of infrastructures, both old and new, it's going on. So there will be a call for papers that has been publicized. That's the letter. And what's relevant here maybe is the dates, right? So the letters of interest should be sent by July 2023, which is this year. And a letter of interest is something very short that states the interest of some community of doing something. So that's where we may think of the dark matter community. The full white papers, then it's a significant effort. They are due in 1 year after that, so July 2020. Then there will be a workshop, and then they will write documents like summaries of all this. So they are trying to mimic this process. It's 2-year process. But again, I think that's only has a chance of succeeding if there is some feedback from the funding agencies and so on. A funny thing is that you have to classify your letters in one of these categories: astroparticles, cosmology, high energy, high intensity, other. That's exactly everything that's connected to dark matter. So should put a different tag like dark matter. Anyway, so one of the things we may try to is write letter of intent, building up all these initiatives on dark matter. So, Thiago, do you want to comment at this point? I'm done with last party.
No, I think I've said pretty much all I wanted before. We can discuss all of the details later.
Okay, so as we discussed this organization, of course we need resources, and I just listed things we can apply to, like FAPERJ, FAPESP, in general, the state foundations. There's, of course, CNPq, CAPES, but there are things like, as we say about Latin America, there is a TWS. Now it's the World Academy of Science. It was Third World Academy of Science. it's the word Academy of Science, but never mind. It's developing word. It's especially for the South. So we may try to get things there. These things funds stuff like travels of people. There is a CLAF, Centro Latino-Americano de Física, which has a short money, but it has some, it works. It has some weight, and people tend to neglect these things. And then, of course, there is a possibility of funding networks, like CAPES sometimes has calls for networks. In Argentina, there is a network called Raíces, where you can connect Argentinians in Argentina with Argentinians abroad. But through these Argentinians abroad, you can make a network, for example, in Latin America. And there is something called the Southern Astrophysics Network, which may connect with dark matter. I'll mention that. And ICTP Safer, as Farinaldo mentioned, is an institution that has a lot of funds in São Paulo, and where you can organize things, events, and they will cover these events. So that's a place where a lot of, Farinaldo mentioned Fabio Yoko, that organized a lot of dark matter meetings there. We organize a school there, and so that's a place that's useful. There is an International Institute of Physics, where Farinaldo is from, which also organized a large dark matter neutrino meeting, I think 2000, maybe 19. There's where I'm currently am, my current institution in ICAS, the International Center for Advanced Studies in San Martin University. We also host events. If you're willing to do something, we can host that event. Okay. So about events, just mention some events that are planned already. So one is this MOCA, which is dark matter in Colombia. It's now, it's on May, but you can, there is a possibility, I understand, of participating remotely. I'm just copying what they circulated. Anyway, you can go to this, get more information on the links. Then, as I mentioned, there is a Southern Astrophysics Network. This is a network between Argentina, Brazil, and Chile, which basically focus on extragalactic astrophysics, mainly galaxy formation. That's like the topic they focus the most. Of course, it's deeply connected to dark matter, as you saw in talks today, for example. So that's a very nice place to foster talks connecting astrophysics to dark matter. The next meeting will be on April. The registration is still open, I think, until March 24, so it's about to close. Take a look at this website, GAN e-group. Well, you can copy this. I can provide the slides. But if you're interested, this meeting will be in Buenos Aires in Argentina, but also in hybrid form like this one. So if you're interested, talk to your peers, also help spread the word. And the big splash at the level of the schools, as Farinaldo was saying, you know, we have to prepare a generation to work with dark matter since it's so new. So you have to go at the bottom, try to get students. So we are organizing next year the dark matter, the International School on Dark Matter and Neutrino Detection. We organized a similar school in 2018, so 6 years ago. It's a 2-week school on neutrino and dark matter. Why? Because there are lots of things in common about the detection, and it's the first week is more theoretical. The second week is all like about detectors and detecting. There are hands-on experiments that you can do. So that's it. It's a big thing for people at the undergraduates or graduate students. We really start from the basics, but they will go up to making their own experiments. So there isn't not a lot of information about this because it's next year. But if you want to have an idea of how this look like, go to this website there, which was the school in 2018, and it will not be much different. But of course, updating with all the new research that happened in the last 6 years. Okay, about popularization, and I think Farinaldo also touched upon that. it's important to raise awareness of everyone about dark matter. And there is something called Dark Matter Day. It's like a joke because it's October 31. It connects with Halloween and so on. But okay, anyway, there is a lot of activity, and I didn't see this in Brazil a lot, but there was some splash in Argentina and in many places in the world. Like talks, there is a planetarium exhibit that's available to every planetarium. It's very nice, like 15 minutes. Everything that you heard in this meeting in 15 minutes for the lay public in a planetarium. So if you can get in touch with people in planetariums and get this working. We did a contest on schools. All the schools, all the public primary schools in Rio de Janeiro were invited, and we had like hundreds of responses drawing by students, and we had we had researchers recording videos. I think Thiago was one of them, Farinaldo was one of them, that were making comments on the videos of the students. Anyway, we invited some people in the community that were available to comment on these drawings of the kids. So it's a good excuse to make a link of the research with the really young people. There is a game which is quite funny, a card game on dark matter detection. In Bariloche, they made even a dark matter ice cream with a company. So they had talks and they had this ice cream, which I did not have the opportunity to taste. So there was a lot of things cross Argentina, Brazil. We had a public school in the Ilha do Governador, talked to a public school in Buenos Aires, kids about dark matter. That was really nice. Anyway, I suggest that if people get mobilized about dark matter, think about, October 21st is long enough that you can plan, but it's short enough that's not in next year. So everyone that wants to plan anything connected to dark matter, there's a lot of things available, a lot of material for this dark matter day. So I think that would be very nice, and undergraduates, everyone can contribute. Okay, so far so good. That's about the dark matter day. There's a website with all this information, past activities. Fine. Let's I talk too much. So let's open microphone now, and after all these discussions, what you people wants to say, and what do you think about what are the possible next steps on that dark matter avenue? Does anyone want to say anything? Okay, good. I think we discussed a lot during the meeting. People are very tired. We are not many that were left. So just would like to thank you all for having participated in the meeting. I don't know if Elisete is there, but we should give her an applause. And I would like to thank, of course, CBPF, all this great infrastructure, so the CBPF direction and the COTEC and so on. But for those that are in the room, we have here Elisete, who organized the coffee breaks and everything connected to secretary of the event. Also, Luan, I think, is there, Rogério. They helped, they made possible everything that you saw in this hybrid thing to make it work. It's a lot of work. So, muito obrigado, Elisete. Muito obrigado, Rogério, Luan. Let's give an applause to them. Thank you so much. Bye-bye.